everyone, welcome to another video by Simplilearn. In this video, we will teach you everything that you need to know about Keras in machine learning and data analysis. To begin, we will explain the concept of Keras to you. We will answer the question, what is Keras and how it is used in deep learning. Then, we will list out some common differences between Keras, TensorFlow, and PyTorch so that you can understand why Keras is the superior framework. After this, we will dive deep into Keras and see how you can use Keras to implement deep learning models with hands-on tutorials. And finally, we will take a look at Keras sequential models, a type of model in Keras which makes implementing neural networks extremely easy. So, let's get started.
The first question that arises in our mind is, what is deep learning? Deep learning is generally considered to be a subset of machine learning, which is nothing but a subset of artificial intelligence. What is artificial intelligence? Artificial intelligence is the intelligence which is demonstrated by machines, unlike the natural intelligence which is displayed by humans and animals, which also involves consciousness and emotionality. Meanwhile, machine learning is an application of artificial intelligence that provides systems the ability to automatically learn and improve from experience without being programmed to specifically. Now, deep learning, as I said, is a class of machine learning algorithms that uses multiple layers to progressively extract higher level features from raw input. For example, if we have a system which we are using for image processing, lower layers in the system may be used to detect the outlines of images, while higher layers may identify the concepts which are relevant to the image. In case of the picture of a human, it might recognize features such as digits or letters or face. Now, in deep learning, we use neural networks to use multiple mathematical operations to break down a complex problem into smaller parts which are solved individually. Each mathematical expression is called a neuron. Deep learning models are trained using large sets of labeled data and neural network architectures that learn features directly from the data without the need for manual feature extraction. One of the most popular types of deep neural networks is known as a convolution neural network. A convolution neural network convolves learned features with input data and uses 2D convolutional layers, making this architecture well suited to processing 2D data such as images. Now, in deep learning, neural networks will play a very important part. What exactly are neural networks? Neural networks are modeled from the way the human brain works. In our brain, we have neurons which carry electrical impulses from our brain to different parts of our body and help in transmitting instructions from the brain all over our body. In neural networks, a neuron acts as nothing more but a mathematical operation. Multiple neurons are required to break down a complex problem into various parts to make it easier to solve. Now, a neural network contains layers of interconnected nodes. Each node in a neural network is a perceptron and is similar to a multiple linear regression. The perceptron feeds the signals which are produced by multiple linear regressions into an activation function that may be nonlinear. Hidden layers will fine-tune the input weightings until neural network's margin of error is minimal and we get the optimal output. Now, what is Keras? Before we move on to Keras, let's take a look at TensorFlow. TensorFlow is a software library which was created by Google to implement large-scale machine learning models and to help solve complex numerical problems. TensorFlow is an end-to-end open-source machine learning platform which you can think of as an infrastructure layer for differentiable programming. It combines 4 key abilities. First, efficiently executing low-level tensor operations on CPU and GPU or TPU, computing gradient of arbitrary differential expressions, scaling computation to many devices, and exporting programs to external runtimes such as servers, browsers, or mobiles. But what does Keras have to do with all of this? Keras is nothing more than a high-level deep learning API which is written in Python for neural networks. It has multiple backend neural network computations and it makes implementing neural networks easy. As we know, Keras is a powerful and easy-to-use free open-source Python library for developing and evaluating deep learning models. Keras is a high-level API of TensorFlow 2. an approachable, highly productive interface for solving machine learning problems with a focus on modern deep learning. It provides essential abstractions and building blocks for developing and shipping machine learning solutions with high iteration velocity. Keras empowers engineers and researchers to take full advantage of the scalability and cross-platform capabilities of TensorFlow 2. You can run Keras on TPU or on large clusters of GPU, and you can export your Keras model to run in the browser or on a mobile device. Keras provides a Python interface for artificial neural networks. Keras acts as an interface for TensorFlow library, and it helps in implementation of commonly used neural network building block layers such as objectives, activation functions, and optimizers, and a host of tools to make working with images and text data easier to simplify the coding necessary for writing deep neural network code. Basically, it wraps efficient numerical computation libraries such as Theano and TensorFlow and allows you to define and train neural network models in just a few lines of code. In fact, TensorFlow and Keras are so tied together that even in TensorFlow, the official Get Started with TensorFlow tutorial, we use high-level Keras APIs embedded in TensorFlow instead of just using TensorFlow by itself. Some of the important features of Keras include Keras being a high-level interface which uses Theano or TensorFlow for its backend. Keras can run smoothly on both CPU and GPU. It supports almost all the models required for you to create a complete neural network. And it is extremely modular in nature, which means it is incredibly expressive, flexible, and apt for innovative research. So why do we need Keras? First of all, Keras is an API which is designed for human beings, not for machines, which means that it follows best practices for reducing cognitive load. It offers consistent and simple APIs. It minimizes the number of users' action required for common use cases, and it provides clear and actionable feedback upon user error. It is extremely powerful and easy to use, and it also wraps numerical computation libraries such as Theano and TensorFlow and allows you to train and define neural networks in a few lines of code. This makes Keras easy to learn and use. As a Keras user, you can be more productive, allowing you to try more ideas than your competition faster, which in turn will help you win machine learning competition. This ease of use does not come at the cost of reduced flexibility because Keras integrates deeply with low-level TensorFlow functionality. It enables you to develop highly hackable workflows where any piece of functionality can be customized or reused easily. Building a model in Keras. Let's take a look at the basic pipeline which you will have to follow when you are using Keras to define a neural network. First of all, you will have to define a neural network. You will have to select the activation functions and the various mathematical operations that are going to be taking place in your neural network along with the different weightages. Next, you will use Keras to compile your network, which is basically you will use Keras to build it. After this, you will fit to your network. You will fit all the training data that you have to your network and use your testing data to evaluate how the network works. Finally, you will use this network to make predictions. This entire 5-step pipeline can be executed in Keras within 2 to 3 lines of code. Neural networks, which would have taken people days or even weeks to make, can be executed in Keras in a couple of hours. Now, uses of Keras. The first use of Keras is to productize deep models on smartphones. Deep models require a lot of computation power to run, but with the help of Keras, we can literally make deep models a product which can be sold and executed on smartphones. The next use of Keras is in distributed training of deep learning models. Distributed training means that we can split our deep learning model into different parts and train it on systems all across the globe. This makes training of our deep learning model extremely fast. Along with saving time, we are also saving on the computational power of our system, as it is not only our system which has to run such a heavy program. By distributing it across various systems, all the resources required to train a deep learning model go down significantly. Before we can see the differences between these platforms, we first need to know what exactly each of these platforms are. Let's start with TensorFlow. What is TensorFlow? TensorFlow is a low-level software library which is created by Google to help implement machine learning models and to solve complex numerical problems. TensorFlow is nothing but a free and open source software library for machine learning. It can be used across a range of tasks but has a particular focus on training and inference of deep neural networks. TensorFlow is a symbolic math library based on data flow and differential programming. It is used for both research and production at Google. What do you mean by data flow? It basically means that we perform calculations by converting every element into graphical form. The variables of the graph are called tensors and mathematical operations are called operators. Here, in the computational graph shown, you can see that x, y, and 2 are the variables. They will also be called tensors, and division, multiplication, and addition are the operators. This graph basically shows us the calculation that is going to occur in a machine learning model where x and y are going to be divided and y and 2 are going to be multiplied. The results of these two calculations are then going to be added to give us the final output. I told you that x, y, and 2 are also called tensors. What exactly are tensors? Tensors are multidimensional arrays with a uniform type. All tensors are immutable like Python numbers and strings, which means that you cannot update the contents of a tensor. You can only create a new tensor. Next, let's look at the API Keras. What exactly is Keras? Keras is a high-level deep learning API written in Python for easy implementation and computation of neural networks. Keras is an open source software library that provides a TensorFlow interface for artificial neural networks. Keras acts as an interface for the TensorFlow library, which means that it runs on top of TensorFlow. Up until version 2.3, Keras supported multiple backends, including TensorFlow, Microsoft Cognitive Toolkit or CNTK, R, Theano, and PlaidML. As of version 2.4, only TensorFlow is supported. Designed to help enable fast experimentation with deep neural networks, it focuses on being user-friendly, modular, and extensible. Keras is a high-level API of TensorFlow, an approachable, highly productive interface for solving machine learning problems with a focus on modern deep learning. It provides essential abstractions and building blocks for developing and shipping machine learning solutions with high iteration velocity. Keras does not perform its own low-level operations such as tensor products and convolution. It relies on backend engines for that. Even though Keras supports multiple backend engines, its primary backend engine is TensorFlow, and its primary supporter is Google, which means that Keras acts as nothing more but a wrapper class around TensorFlow, Theano, CNTK, PlaidML, or MXNet, which are low-level APIs. Next, we will look at PyTorch. What exactly is PyTorch? PyTorch is a low-level API which is developed by Facebook for natural language processing and computer vision. It is a more powerful version of NumPy. It is an open-source machine learning library based on the Torch library used for applications such as computer vision and natural language processing. Primarily developed by Facebook's AI Research Lab, it is free and open-source software released under the modified BSD license. Although the Python interface is a more polished and the primary focus of development, PyTorch also has a C++ interface. Python is a widely liked language because it is easy to understand and write. PyTorch emphasizes flexibility and allows deep learning models to be expressed in basic Python. PyTorch is mainly used for natural language processing and for computer vision. Now let's move on to the differences between TensorFlow, Keras, and PyTorch. The first difference that we'll be looking at is called level of API. There are two main types of APIs, a low-level API and a high-level API. API stands for Application Programming Interface. A low-level application programming interface is generally more detailed and allows you to have more detailed control to manipulate functions within them on how to use and implement them. while a high-level API is more generic and simple and provides more functionality with one command statements than a lower-level API. High-level interfaces are comparatively easier to learn and to implement the models using them. They allow you to write code in a shorter amount of time and to be less involved with the details. In this case, TensorFlow is a high and low-level API. Pure TensorFlow is a low-level API, while TensorFlow wrapped in Keras is a high-level API. Keras in itself is a high-level API which uses multiple low-level APIs as a backend and simplifies the operation of these low-level APIs. PyTorch is a low-level API. The next criteria that we'll be looking at is speed. TensorFlow is very fast and is used for high performances. Keras is slower as it works on top of TensorFlow. Not only does it have to wait for TensorFlow to finish implementation, it then starts its own implementation. Meanwhile, PyTorch works at the same speed as TensorFlow, as both of them are both low-level APIs. Now, Keras is a wrapper class for TensorFlow and has added abstraction functionalities on top of TensorFlow, which make it slower than TensorFlow and PyTorch. In computation speed, both TensorFlow and PyTorch are almost equal, and in development speed, Keras is faster as it has built-in functionalities which can significantly reduce your development time. The next difference is on the architecture. TensorFlow is not very easy to use, and even though it provides Keras as a framework that makes it work easier, TensorFlow still has a very complex architecture which is hard to use. Meanwhile, Keras has a simpler architecture and is easier to use. It provides a high level of abstraction which makes implementation of programs in Keras significantly easier. PyTorch, on the other hand, also has a complex architecture and the readability is less when compared to Keras. TensorFlow uses computational graphs which makes it very complex and hard to interpret, but it has amazing computational ability across platforms. PyTorch is a little hard for beginners but is really good for computer vision and deep learning purposes. Datasets and debugging. TensorFlow works with large datasets due to its high execution speed, and debugging is really hard in TensorFlow due to its complex nature. Meanwhile, Keras only works with very small datasets as its speed of execution is low. Programs do not require frequent debugging in Keras as they are relatively simpler, and PyTorch can manage high-level tasks in higher dimension datasets and is easier to debug than both Keras and TensorFlow. Next, we'll be looking at ease of development. As we said before, TensorFlow works with many hard concepts such as computational graphs and tensors, which means that writing code in TensorFlow is very hard. It is generally used by people when they are doing research work and really need very specific functionalities. Keras, on the other hand, provides a high level of abstraction which makes it very easy to use. It is best for people who are just starting out with Python and machine learning. PyTorch is easier than TensorFlow but is still comparatively hard than Keras. It is not very easy to learn for beginners but is significantly more powerful than just plain Keras. Ease of deployment. TensorFlow is very easy to deploy as it uses TensorFlow serving. TensorFlow Serving is a flexible, high-performance serving system for machine learning models designed for production environments. TensorFlow Serving makes it easy to deploy new algorithms and experiments while keeping the same server architecture and APIs. TensorFlow Serving provides out-of-the-box integration with TensorFlow models but can be easily extended to serve other types of models and data. In Keras, model deployment can be done with either TensorFlow Serving or Flask, which makes it relatively easy but not as easy as it would be with TensorFlow and PyTorch. PyTorch uses PyTorch Mobile, which makes deployment easy, but again, for TensorFlow deployment is way easier as TensorFlow Serving can update your machine learning backend on the fly without the user even realizing. There's a growing need to execute ML models on edge devices to reduce latency, preserve privacy, and enable new interactive use cases. In the past, engineers used to train models separately. They would then go through a multi-step, error-prone, and often complex process to train the models for execution on a mobile device. The mobile runtime was often significantly different from the operations available during training, leading to inconsistent developer and eventually user experience. All of these frictions have been removed by PyTorch Mobile by allowing a seamless process to go from training to deployment by staying entirely within the PyTorch ecosystem. It provides an end-to-end workflow that simplifies the research to production environment for mobile devices. In addition, it paves the way for privacy-preserving features via federated learning techniques. At the end of the day, the question that really matters is which framework should you use, Keras, TensorFlow, or PyTorch? Now, TensorFlow has implemented various levels of abstraction to make implementation of deep learning and neural networks easy. This has also made debugging easier. Keras is simple and easy, but not as fast as TensorFlow. It is more user-friendly than any other deep learning API, however, and is easier to learn for beginners. PyTorch, on the other hand, is the preferred deep learning API for teachers, but it is not as widely used in production as TensorFlow is. It is faster, but it has lower GPU utilization. At the end of the day, the framework that we would suggest that you use is TensorFlow. Why? While PyTorch may have been the preferred deep learning library for researchers, TensorFlow is much more widely used in day-to-day production. PyTorch's ease of use combined with the default eager execution mode for easier debugging predestines it to be used for fast, hacky solutions and smaller scale models. But TensorFlow's extensions for deployment on both servers and mobile devices, combined with the lack of Python overhead, makes it the preferred option for companies that work with deep learning models. In addition, the TensorFlow board visualization features offers a nice way of showing the inner workings of your model to, say, your customers. Meanwhile, between TensorFlow and Keras, the main difference isn't in performance. TensorFlow is a bit faster due to less overhead, but also the level of control you would like. Keras is much easier to start with than plain TensorFlow, but if you want to do something with Keras that doesn't come out of the box, it will be harder to implement that. TensorFlow, on the other hand, allows you to create any arbitrary computational graph, providing much more flexibility. So if you're doing more research type of work, TensorFlow is the sure route to go due to the flexibility that it provides.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
So we're going to dive right into what is Keras. We'll also go all the way through this into a couple of tutorials because that's where you really learn a lot, is when you roll up your sleeves. So when we talk about what is Keras, Keras is a high-level deep learning API written in Python for easy implementation of neural networks. It uses deep learning frameworks such as TensorFlow, PyTorch, etc. as backend to make computation faster. And this is really nice because as a programmer, there is so much stuff out there and it's evolving so fast, it can get confusing. And having some kind of high-level order in there where you can actually view it and easily program these different neural networks is really powerful. It's really powerful to have something out really quick and also be able to start testing your models and seeing where you're going. So Keras works by using complex deep learning frameworks such as TensorFlow, PyTorch, MLPlaid, etc. as a backend for fast computation, while providing a user-friendly and easy-to-learn front-end. And you can see here we have the Keras API specifications, and under that you'd have like TF Keras for TensorFlow, Thano Keras, and so on. And then you have your TensorFlow workflow that this is all sitting on top of. And this is, like I said, it organizes everything. The heavy lifting is still done by TensorFlow or whatever underlying package you put in there. And this is really nice because you don't have to dig as deeply into the heavy end stuff while still having a very robust package you can get up and running rather quickly. And it doesn't distract from the processing time because all the heavy lifting is done by packages like TensorFlow. This is the organization on top of it. So the working principle of Keras. The working principle of Keras is Keras uses computational graphs to express and evaluate mathematical expressions. And you can see here we put them in blue. They have the expression expressing complex problems as a combination of simple mathematical operators, where we have like the percentage, or in this case in Python that's usually your remainder, or multiplication. You might have the operator of x to the power of 0.3. And it is useful for calculating derivatives by using back propagation. So if we're doing with neural networks, when we send the error back up to figure out how to change it, this makes it really easy to do that without really not banging your head and having to hand write everything. It's easier to implement distributed computation, and for solving complex problems, specify input and outputs and make sure all nodes are connected. And so this is really nice as you come in through, is that as your layers are going in there, you can get some very complicated different setups nowadays, which we'll look at in just a second. And this just makes it really easy to start spinning this stuff up and trying out the different models. So when we look at Keras models, Keras model, we have a sequential model. Sequential model is a linear stack of layers where the previous layer leads into the next layer. And this, if you've done anything else, even like the sklearn with their neural networks and propagation and any of these setups, this should look familiar. You should have your input layer, it goes into your layer 1, layer 2, and then to the output layer. And it's useful for simple classifier or decoder models. And you can see down here we have the model equals a Keras sequential, and this is the actual code. You can see how easy it is. We have a layer that's dense, your layer 1. As an activation, they're using the ReLU in this particular example. And then you have your name layer 1, layer dense ReLU, name layer 2, and so forth. And they just feed right into each other, so it's really easy just to stack them, as you can see here, and it automatically takes care of everything else for you. And then there's a functional model. And this is really where things are at. This is new. Make sure you update your Keras, or you'll find yourself running this, doing the functional model. You'll run into an error code because this is a fairly new release. And it uses multi-input and multi-output model. The complex model, which forks into 2 or more branches. And you can see here we have our image inputs equals your Keras input shape equals 32 by 32 by 3. You have your dense layers, dense 64 activation ReLU. This should look similar to what you already saw before, but if you look at the graph on the right, it's going to be a lot easier to see what's going on. You have 2 different inputs. And one way you could think of this is maybe one of those is a small image and one of those is a full-sized image. And that feedback goes into, you might feed both of them into one node because it's looking for one thing, and then only into one node for the other one. And so you can start to get kind of an idea that there's a lot of use for this kind of split and this kind of setup. We have multiple information coming in, but the information's very different even though it overlaps. And you don't want it to send it through the same neural network. And they're finding that this trains faster and also has a better result depending on how you split the data up and how you fork the models coming down. And so in here we do have the 2 complex models coming in. We have our image inputs, which is a 32 by 32 by 3, or 3 channels, or 4 if you're having an alpha channel. You have your dense, your layers, dense is 64 activation using the ReLU, very common. X equals dense inputs, X layers dense X64 activation equals ReLU, X outputs equals layers dense 10X, model equals Keras, model inputs equals inputs, outputs equals outputs, name equals NINST model. So we add a little name on there. And again, this is this kind of split here. This is setting us up to have the input go into different areas. So if you're already looking at Keras, you probably already have this answer. What are neural networks? But it's always good to get on the same page, and for those people who don't fully understand neural networks, to dive into them a little bit or do a quick overview. Neural networks are deep learning algorithms modeled after the human brain. They use multiple neurons, which are mathematical operations, to break down and solve complex mathematical problems. And so just like the neuron, one neuron fires in and it fires out to all these other neurons, or nodes as we call them, and eventually they all come down to your output layer. And you can see here we have the really standard graph: input layer, a hidden layer, and an output layer. One of the biggest parts of any data processing is your data pre-processing. So we always have to touch base on that. With a neural network, like many of these models, they're kind of, when you first start using them, they're like a black box. You put your data in, you train it, and you test it and see how good it was. And you have to pre-process that data because bad data in is bad outputs. So in data pre-processing, we will create our own data examples set with Keras. The data consists of a clinical trial conducted on 2,100 patients, ranging from ages 13 to 100, with the patients under 65 and the other half over 65 years of age. We want to find the possibility of a patient experiencing side effects due to their age. And you can think of this in today's world with COVID, what's going to happen on there. And we're going to go ahead and do an example of that in our live hands-on. Like I said, most of this you really need to have hands-on to understand. So let's go ahead and bring up our Anaconda and open that up and open up a Jupyter Notebook for doing the Python code in. Now, if you're not familiar with those, you can use pretty much any of your setups. I just like those for doing demos and showing people, especially shareholders. It really helps because it's a nice visual. So let me go ahead and flip over to our Anaconda. And the Anaconda has a lot of cool tools. They just added Datalore and IBM Watson Studio Cloud into the Anaconda framework. But we'll be in the Jupyter Lab or Jupyter Notebook. I'm going to do Jupyter Notebook for this because I use the lab for like large projects with multiple pieces because it has multiple tabs, where the notebook will work fine for what we're doing. And this opens up in our browser window because that's how Jupyter Notebook is set to run. And we'll go under New, create a new Python 3, and it creates an untitled Python. We'll go ahead and give this a title, and we'll just call this Keras tutorial. And let's change that to capital. There we go. We'll go ahead and just rename that. And the first thing we want to go ahead and do is get some pre-processing tools involved. And so we need to go ahead and import some stuff for that, like our NumPy, do some random number generation. I mentioned sklearn or your scikit. If you're installing sklearn, the sklearn stuff, it's scikit you want to look up. That should be a tool of anybody who is doing data science. If you're not familiar with the sklearn toolkit, it's huge, but there's so many things in there that we always go back to. And we want to go ahead and create some train labels and train samples for training our data. And then just a note of what we're actually doing in here. Let me go ahead and change this. This is kind of a fun thing you can do. We can change the code to Markdown. And then Markdown code is nice for doing examples once you've already built this. Our example data, we're going to do experimental. There we go. Experimental drug was tested on 2,100 individuals between 13 to 100 years of age. Half the participants are under 65, and 95% of participants are under 65. Experienced no side effects, while 95% of participants over 65 experienced side effects. So that's kind of where we're starting at. And this is just a real quick example, because we're going to do another one with a little bit more complicated information. And so we want to go ahead and generate our setup. So we want to do for I in range, and we want to go ahead and create, if you look here, we have random integers, train the labels, append. So we're just creating some random data. And let me go ahead and just run that. And so once we've created our random data, and you can certainly ask for a copy of the code from Simplilearn. They'll send you a copy of this, or you can zoom in on the video and see how we went ahead and did our train samples, append, and we're just using this. I do this kind of stuff all the time. I was running a thing on that had to do with errors following a bell-shaped curve on a standard distribution error. And so what do? I generate the data on a standard distribution error to see what it looks like and how my code processes it, since that was the baseline I was looking for. In this, we're just doing generating random data for our setup on here. And we could actually go in, print some of the data up. Let's just do this, print. We'll do train samples, And we'll just do the first 5 pieces of data in there to see what that looks like. And you can see the first 5 pieces of data in our trained samples is 49, 85, 41, 68, 19. Just random numbers generated in there. That's all that is. And we generated significantly more than that. Let's see, 50 up here, 1,000. Yeah, so there's 1,000 here. 1,000 numbers we generated. And we could also, if we wanted to find that out, we could do a quick print the length of it. And so, or you could do a shape kind of thing, and if you're using NumPy, although the link for this is just fine. And there we go, it's actually 2100, like we said in the demo setup in there. And then we want to go ahead and take our labels. Oh, that was our train labels. We also did samples, didn't we? So we could also print, do the same thing. Oh, labels. And let's change this to labels. And labels. And run that just to double check, and sure enough we have 2100 and they're labeled 10, 10, 10. I guess that's if they have symptoms or not. 1 symptoms, 0 none. And so we want to go ahead and take our train labels and we'll convert it into a NumPy array, and the same thing with our samples. And let's go ahead and run that. And we also shuffle. This is just a neat feature you can do in NumPy right here. Put my drawing thing on, which I didn't have on earlier. I can take the data and I can shuffle it. So we have our, so it just randomizes it. That's all that's doing. We've already randomized it, so it's kind of an overkill. It's not really necessary. But if you're doing a larger package where the data is coming in, and a lot of times it's organized somehow, and you want to randomize it just to make sure that you know, the input doesn't follow a certain pattern that might create a bias in your model. And we go ahead and create a scalar. The scalar range, minimum max scalar, feature range 0 to 1. And then we go ahead and scale the scaled trained samples. So we're going to go ahead and fit and transform the data so it's nice and scaled. And that is the age. So you can see up here we have 49, 85, 41. We're just moving that so it's going to be between 0 and 1. And so this is true with any of your neural networks. You really want to convert the data to 0 and 1, otherwise you create a bias. So if you have like 100 creates a bias versus the math behind it gets really complicated. If you actually start multiplying stuff, there's a lot of multiplication and addition going on in there, that higher end value will eventually multiply down, and it will have a huge bias as to how the model fits it, and then it will not fit as well. And then one of the fun things we can do in Jupyter Notebook is that if you have a variable and you're not doing anything with it, and it's the last one on the line, it will automatically print. And we're just going to look at the first 5 samples on here, and so it's going to print the first 5 samples. And you can see, here we go, 0.9195, 0.791, so everything's between 0 and 1. And that just shows us that we scaled it properly and it looks good. It really helps a lot to do these kind of print-ups halfway through. You never know what's going to go on there. I don't know how many times I've gotten down and found out that the data sent to me that I thought was scaled was not. And then I have to go back and track it down and figure it out on there. So let's go ahead and create our artificial neural network. And for doing that, this is where we start diving into TensorFlow and Keras. TensorFlow, if you don't know the history of TensorFlow, it helps to jump into, we'll just use Wikipedia. Careful, don't quote Wikipedia on these things because you get in trouble. But it's a good place to start. Back in 2011, Google Brain built Disbelief as a proprietary machine learning setup. TensorFlow became the open source for it. So TensorFlow was a Google product, and then it became open sourced, and now it's just become probably one of the de factos when it comes for neural networks as far as where we're at. So when you see the TensorFlow setup, it's got like a huge following. There are some other setups like the Scikit under the sklearn has their own little neural network, but the TensorFlow is the most robust one out there right now. And Keras sitting on top of it makes it a very powerful tool, so we can leverage both the Keras easiness in which we can build a sequential setup on top of TensorFlow. And so in here we're going to go ahead and do our input of TensorFlow, and then we have the rest of this is all Keras here from number 2 down. We're going to import from TensorFlow the Keras connection, and then you have your TensorFlow Keras models, import sequential. It's a specific kind of model. We'll look at that in just a second. If you remember from the files, that means it goes from one layer to the next layer to the next layer. There's no funky splits or anything like that. And then we have from TensorFlow Keras layers, we're going to import our activation and our dense layer. And we have our optimizer, Atom. This is a big thing to be aware of, how you optimize your data. When you first do it, Atom's as good as any. Atom is usually, there's a number of optimizer out there. There's a couple of main ones, but Atom is usually assigned to bigger data. It works fine. Usually the lower data does it just fine, but Atom is probably the mostly used. But there are some more out there, and depending on what you're doing with your layers, your different layers might have different activations on them. And then finally down here you'll see our setup where we want to go ahead and use the metrics. And we're going to use the TensorFlow Keras metrics for categorical cross entropy. So we can see how everything performs when we're done. That's all that is. A lot of times you'll see us go back and forth between TensorFlow, and then Scikit has a lot of really good metrics also for measuring these things. Again, it's the end of the at the end of the story, how good does your model do? And we'll go ahead and load all that. And then comes the fun part. I actually like to spend hours messing with these things. And 4 lines of code. You're like, you're going to spend hours on 4 lines of code? No, we don't spend hours on 4 lines of code. That's not what we're talking about when I say spend hours on 4 lines of code. What we have here, I'm going to explain that in just a second. We have a model, and it's a sequential model. If you remember correctly, we mentioned the sequential up here where it goes from one layer to the next. And our first layer is going to be your input. It's going to be what they call dense, which is usually it's just dense, and then you have your input and your activation. How many units are coming in? We have 16. What's the shape? What's the activation? And this is where it gets interesting, because we have in here ReLU on 2 of these and softmax activation on 1 of these. There are so many different options for what these mean and how they function. How does the ReLU, how does the softmax function? And they do a lot of different things. We're not going to go into the activations in here. That is what really you spend hours doing, is looking at these different activations. And just some of it is just almost like you're playing with it like an artist. You start getting a feel for like a inverse tangent activation, or the tanh activation. Takes up a huge processing amount, so you don't see it a lot. Yet it comes up with a better solution, especially when you're doing when you're analyzing Word documents and you're tokenizing the words. And so you'll see this shift from one to the other because you're both trying to build a better model. And if you're working on a huge data set, it'll crash the system. It'll just take too long to process. And then you see things like softmax. Softmax generates an interesting setup where a lot of these, when you talk about ReLU, oops, let me do this. ReLU, there we go. ReLU has a setup where if it's less than 0, it's 0, and then it goes up. And then you might have what they call lazy setup, where it has a slight negative to it so that the errors can translate better. Same thing with softmax. It has a slight laziness to it so that errors translate better. All these little details make a huge difference on your model. So one of the really cool things about data science that I like is you build your what they call you build to fail. And it's an interesting design setup. Oops, I forgot the end of my code here. The concept of build to fail is you want the model as a whole to work, so you can test your model out. So that you can do, you can get to the end and you can do your, let's see, where was it? Overshot down here. You can test out the quality of your setup on there. And see, where did I do my TensorFlow? Oh, here we go. It was right above me. There we go. We start doing your cross entropy and stuff like that. Is you need a full functional set of code so that when you run it, you can then test your model out and say, hey, it's either this model works better than this model and this is why. And then you can start swapping in these models. And so when I say I spend a huge amount of time on pre-processing data, it's probably 80% of your programming time. Well, between those two, it's like 80-20. You'll spend a lot of time on the models. Once you get the model down, once you get the whole code and the flow down set, depending on your data, your models get more and more robust as you start experimenting with different inputs, different data streams, and all kinds of things. And we can do a simple model summary here. Here's our sequential, here's our layer, our output, our parameter. This is one of the nice things about Keras is you can see right here, here's our sequential 1 model. Boom, 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 boom. Everything's set and clear and easy to read. So once we have our model built, the next thing we're going to want to do is we're going to go ahead and train that model. And so the next step is, of course, model training. And when we come in here, this a lot of times is just paired with the model because it's so straightforward. It's nice to print out the model setup so you can have a tracking. But here's our model. The keyword in Keras is compile, optimizer atom, learning rate, another term right there that we're just skipping right over that really becomes the meat of the setup is your learning rate. So whoops, I forgot that I had an arrow, but I'll just underline it. A lot of times the learning rate set to 0.01. Depending on what you're doing, this learning rate can overfit and underfit. So you'd want to look up, I know we have a number of tutorials out on overfitting and underfitting that are really worth reading once you get to that point and understanding. And we have our loss, sparse categorical cross entropy. So this is going to tell Keras how far to go until it stops. And then we're looking for metrics of accuracy. So we'll go ahead and run that. And now that we've compiled our model, we want to go ahead and run it, fit it. So here's our model fit. We have our scaled train samples, our train labels, our validation split. In this case, we're going to use 10% of the data for validation. Batch size, another number you kind of play with. Not a huge difference as far as how it works, but it does affect how long it takes to run, and it can also affect the bias a little bit. Most of the time, though, a batch size is between 10 to 100, depending on just how much data you're processing in there. We want to go ahead and shuffle it. We're going to go through 30 epochs and put a verbose of 2. Let me just go ahead and run this. And you can see right here, here's our epoch, here's our training, here's our loss. Now, if you remember correctly up here, we set the loss. Let's see, where was it? Compiled our data. There we go, loss. So it's looking at the sparse categorical cross entropy. This tells us that as it goes, how much does the error go down? Is the best way to look at that. And you can see here, the lower the number, the better. It just keeps going down. And vice versa, accuracy we want. Let's see, where's my accuracy? Value accuracy at the end. And you can see 0.619, 0.69, 0.74, it's going up. We want the accuracy, would be ideal if it made it all the way to 1. But we also, the loss is more important because it's a balance. You can have 100% accuracy and your model doesn't work because it's overfitted. Again, you want to look up overfitting and underfitting models. And we went ahead and went through 30 epochs. it's always fun to kind of watch your code going. To be honest, I usually the first time I run it, I'm like, oh, that's cool, I get to see what it does. And after the second time of running it, I'm like, I'd like to just not see that. And you can repress those, of course, in your code. Repress the warnings in the printing. And so the next step is going to be building a test set and predicting it now. So here we go. We want to go ahead and build our test set. And we have, just like we did our training set, a lot of times you just split your initial set up. But we'll go ahead and do a separate set on here. And this is just what we did above. There's no difference as far as the randomness that we're using to build this set on here. The only difference is that we already did our scalar up here. Well, that doesn't matter because the data is going to be across the same thing. But this should just be transform down here instead of fit transform. Because you don't want to refit your data on your testing data. There we go. And now we're just transforming it because you never want to transform the test data. Easy mistake to make, especially on an example like this where we're not doing, we're randomizing the data anyway, so it doesn't matter too much because we're not expecting something weird. And then we want to go ahead and do our predictions. The whole reason we built the model is we take our model, we predict, and we're going to do, here's our X-scale data, batch size 10, verbose, and now we have our predictions in here, and we could go ahead and do a, we'll print predictions, and then I guess I could just put down predictions in 5 so we can look at the first 5 of the predictions. And what we have here is we have our age and the prediction on this age versus what we think it's going to be, what we think is going to they're going to have symptoms or not. And the first thing we notice is that's hard to read because we really want a yes/no answer. So we'll go ahead and just round off the predictions using the argmax, the NumPy argmax for predictions. So it just goes to a 0, 1, and if you remember, this is Jupyter Notebook, so I don't have to put the print. I can just put in rounded predictions, and we'll just do the first 5. And you can see here 0, 1, 0, 0, 0. So that's what the predictions are that we have coming out of this. Is no symptoms, symptoms, no symptoms, symptoms, no symptoms. And just as we were talking about at the beginning, we want to go ahead and take a look at this. There we go. Confusion matrices for accuracy check. Most important part when you get down to the end of the story, how accurate is your model before you go and play with the model and see if you can get a better accuracy out of it. And for this, we'll go ahead and use the scikit, the sklearn metrics, scikit being where that comes from. Import confusion matrix, some iteration tools, and of course a nice matplot library. That makes a big difference, so it's always nice to have a nice graph to look at. Picture's worth 1,000 words. And then we'll go ahead and call it CM for confusion matrix, y true equals test labels, y predict rounded predictions. And we'll go ahead and load in our CM. And I'm not going to spend too much time on the plotting, going over the different plotting code. You can spend we have whole tutorials on how to do your different plotting on there. But we do have here is we're going to do a plot confusion matrix. There's our CM, our classes, normalized false, title, confusion matrix. CMAP is going to be in blues. And you can see here we have to the nearest CMAP, titles, all the different pieces, whether you put tick marks or not, the marks, the classes, the color bar. So a lot of different information on here as far as how we're doing the printing of the confusion matrix. You can also just dump the confusion matrix into a Seaborn and real quick get an output. It's worth knowing how to do all this. When you're doing a presentation to the shareholders, you don't want to do this on the fly. You want to take the time to make it look really nice, like our guys in the back did. And let's go ahead and do this. Forgot to put together our CM plot labels. We'll go ahead and run that. and then we'll go ahead and call the definition for our mapping. And you can see here, plot confusion matrix. That's the little script we just wrote, and we're going to dump our data into it. So our confusion matrix, our classes, title confusion matrix, and let's just go ahead and run that. And you can see here we have our basic setup. No side effects 195, had side effects 200, no side effects that had side effects. So we predicted the 10 of them who actually had side effects, and that's pretty good. I mean, I don't know about you, but you know, that's 5% error on this, and this is because there's 200 here. That's where I get 5% is. Divide these both by 2, and you get 5 out of 100. You can do the same kind of math up here. Not as quick on the fly because it's 15 and 195, not an easily rounded number. But you can see here where they have 15 people who predicted to have with the no side effects but had side effects kind of set up on there. And these confusion matrix are so important at the end of the day. This is really where you show whatever you're working on comes up, and you can actually show them, hey, this is how good we are or not, how messed up it is. So this was I spent a lot of time on some of the parts, but you can see here is really simple. We did the random generation of data, but when we actually built the model coming up here, here's our model summary, and we just have the layers on here that we built with our model on this, and then we went ahead and trained it and ran the prediction. Now we can get a lot more complicated. Let me flip back on over here because we're going to do another demo. So that was our basic introduction to it. We talked about the oops, here we go. Okay, so implementing a neural network with Keras. After creating our samples and labels, we need to create our Keras neural network model. We will be working with a sequential model which has 3 layers. And this is what we did. We had our input layer, our hidden layers, and our output layers. And you can see the input layer coming in was the age factor. We had our hidden layer, and then we had the output. Are you going to have symptoms or not? So we're going to go ahead and go with something a little bit more complicated. Training our model is a 2-step process. We first compile our model, and then we train it in our training data set. So we have compiling. Compiling converts the code into a form of understandable by machine. We used the ADAM in the last example, a gradient descent algorithm, to optimize the model, and then we trained our model, which means it let it learn on training data. And I actually had a little backwards there, but this is what we just did. Is if you remember from our code we just had, oops, let me go back here. Here's our model that we created, summarized. We come down here and we compile it. So it tells it, hey, we're ready to build this model and use it. And then we train it. And this is the part where we go ahead and fit our model and put that information in here, and it goes through the training on there. And of course we scaled the data, which was really important to do. And then you saw we did the creating a confusion matrix with Keras. As we are performing classifications on our data, we need a confusion matrix to check the results. A confusion matrix breaks down the various misclassifications as well as correct classifications to get the accuracy. And so you can see here, this is what we did with the true positive, true negative, false negative. And that is what we went over. Let me just scroll down here. On the end, we printed it out, and you can see we have a nice printout of our confusion matrix with the true positive, false negative, true negative. And so the blue ones, we want those to be the biggest numbers because those are the better side. And then we have our false predictions on here as far as this one. So it had no side effects, but we predicted, let's see, no side effects predicting side effects and vice versa.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Now, saving and loading models with Keras. We're going to dive into a more complicated demo. And you're going to say, oh, well, that was a lot of complication before. Well, if you broke it down, we randomized some data, we created the Keras setup, we compiled it, we trained it, we predicted, and we ran our matrix. So we're going to dive into something a little bit more fun. Is we're going to do a face mask detection with Keras. So we're going to build a Keras model to check if a person is wearing a mask or not in real time. And this might be important if you're at the front of a store. This is something today which is might be very useful as far as some of our, making sure people are safe. And so we're going to look at mask and no mask. And let's start with a little bit on the data. And so in my data I have with a mask. You can see they just have a number of images showing the people in masks. And again, if you want some of this information, contact Simplilearn, and they can send you some of the information as far as people with and without masks, so you can try it on your own. And this is just such a wonderful example of this setup on here. So before I dive into the mask detection, talking about being in the current with COVID and seeing if people are wearing masks, this particular example I had to go ahead and update to a Python 3.8 version. It might run in a 3.7, I'm not sure. I kind of skipped 3.7 and installed 3.8. So I'll be running in a Python 3.8, and then you also want to make sure your TensorFlow is up to date, because they call functional layers, that's where they split, if you remember correctly from back. Let's take a look at this. Remember, from here, the functional model and a functional layer allows us to feed in the different layers into different nodes into different layers and split them. Very powerful tool, very popular right now in the edge of where things are with neural networks and creating a better model. So I've upgraded to Python 3.8, and let's go ahead and open that up and go through our next example, which includes multiple layers, programming it to recognize whether someone wears a mask or not, and then saving that model so we can use it in real time. So we're actually almost a full end-to-end development of a product here. Of course, this is a very simplified version, and there'd be a lot more to it. You'd also have to do recognizing whether it's someone's face or not. All kinds of other things go into this. So let's go ahead and jump into that code, and we'll open up a new Python 3. Oops, Python 3. It's working on it. There we go. And then we want to go ahead and train our mask. We'll just call this train mask. And we want to go ahead and train mask and save it. So it's save mask, train mask detection, not to be confused with masking data. A little bit different. We're actually talking about a physical mask on your face. And then from the Keras standpoint, we got a lot of imports to do here. And I'm not going to dig too deep on the imports. We're just going to go ahead and notice a few of them. So we have in here, oops, let me go Alt-D, there we go. Have something to draw with a little bit here. We have our image processing, and the image processing right here, let me underline that, deals with how do we bring images in, because most images are like a square grid, and then each value in there has 3 values for the 3 different colors. Keras and TensorFlow do a really good job of working with that, so you don't have to do all the heavy listening and figuring out what's going to go on. And we have the MobileNet average pooling, 2D. This again is how do we deal with the images and pulling them. Dropout's a cool thing worth looking up. If you haven't, as you get more and more into Keras and TensorFlow, it'll auto drop out certain nodes. That way you'll get a better, the nodes just kind of die. They find that they actually create more of a bias than a help, and they also add processing time, so they remove them. And then we have our flatten. That's where you take that huge array with the 3 different colors and you find a way to flatten it so it's just a one-dimensional array instead of a 2 by 2 by 3. Dense input, we did that in the other one, so that should look a little familiar. Oops, there we go. Our input, our model. Again, these are things we had on the last one. Here's our optimizer with our atom. We have some pre-processing on the input that goes along with bringing in the data in. More pre-processing with image to array, loading the image, This stuff is so nice. It looks like a lot of work. So you have to import all these different modules in here. But the truth is it does everything for you. You're not doing a lot of pre-processing. You're letting the software do the pre-processing. And we're going to be working with the setting something to categorical. Again, that's just a conversion from a number to a category. 0, 1 doesn't really mean anything. It's like true, false. Label binarizer, the same thing. We're changing our labels around. And then there's our train test split classification report. Our IM utilities, let me just go ahead and scroll down here a notch for these. This is something a little different going on down here. This is not part of the TensorFlow or the sklearn. This is the scikit setup in TensorFlow above. The paths, this is part of OpenCV. And we'll actually have another tutorial going out with the OpenCV. So if you want to know more about OpenCV, you'll get a glance on it in this software, especially the second piece when we reload up the data and hook it up to a video camera. We're going to do that on this round. But this is part of the OpenCV thing, and you'll see CV2 is usually how that's referenced. But the IM utilities has to do with how do you rotate pictures around and stuff like that, and resize them. And then the matplot library for plotting, because it's nice to have a graph, tells us how good we're doing, and then of course our NumPy numbers array and just a straight OS access. Wow, so that was a lot of imports. Like I said, I'm not going to I spent a little time going through them, but we didn't want to go too much into them. And then I'm going to create some variables that we need to go ahead and initialize. We have the learning rate, number of epochs to train for, and the batch size. And if you remember correctly, we talked about the learning rate to the negative 4.00001. A lot of times it's 0.001 or 0.001. Usually it's in that variation depending on what you're doing and how many epochs, and they kind of play with the epochs. The epochs is how many times we're going to go through all the data. And now I have it as 2. The actual setup is for 20, and 20 works great. The reason I have it for 2 is it takes a long time to process. One of the downsides of Jupyter is that Jupyter isolates it to a single kernel. So even though I'm on an 8-core processor with 16 dedicated threads, only one thread is running on this, no matter what. So it doesn't matter. So it takes a lot longer to run, even though TensorFlow really scales up nicely. And the batch size is how many pictures do we load at once and process. Again, those are numbers you have to learn to play with depending on your data and what's coming in. And the last thing we want to go ahead and do is there's a directory with a data set we're going to run. And this just has images of masks and not masks. And if we go in here, you'll see data set. And then you have pictures with masks. They're just images of people with masks on their face. And then we have the opposite. Let me go back up here. Without masks. So it's pretty straightforward. They look kind of askew because they tried to format them into very similar setup on there. So they're mostly squares. You'll see some that are slightly different on here. And that's kind of an important thing to do on a lot of these data sets. Get them as close as you can to each other. And we actually will run in this processing of images up here, and the Keras layers and importing and dealing with images. It does such a wonderful job of converting these that a lot of it we don't have to do a whole lot with. So you have a couple things going on there. And so we're now going to be, this is now loading the images, and let me see. And we'll go ahead and create data and labels. Here's our here's the features going in, which is going to be our pictures, and our labels going out. And then for categories in our list directory, and if you remember, I just flashed that at you. It had face mask or no face mask. Those are the two options. And we're just going to load into that. We're going to append the image itself and the labels. So we're just going to create a huge array. And you can see right now this could be an issue if you had more data. At some point, thankfully I have a 32 gig hard drive or RAM. Even that, you could do with a lot less of that. Probably under 16 or even 8 gigs would easily load all this stuff. And there's a conversion going on in here. I told you about how we are going to convert the size of the image so it resizes all the images. And that way our data is all identical the way it comes in. And you can see here with our labels, we have without mask, without mask, without mask. The other one would be with mask. Those are the two that we have going in there. And then we need to change it to the one-hot encoding. And this is going to take our, up here we had, what was it, labels and data. We want the labels to be categorical. So we're going to take labels and change it to categorical, and our labels then equal a categorical list. We'll run that. And again, if we do labels and we just do the last or the first 10, let's do the last 10 just because minus 10 to the end. There we go. Just so we can see what the other side looks like. We now have 1. That means they have a mask. 1, 0, 1, 0, so on. 1 being they have a mask, and 0 no mask. And if we did this in reverse, I just realized that this might not make sense if you've never done this before. Let me run this. 0, 1. So 0 is, do they have a mask on? 0. Do they not have a mask on? 1. So this is the same as what we saw up here without mask. 1 equals, the second value is without mask. So with mask, without mask. And that's just with any of your data processing, we can't really, if you have a 0, 1 output, it causes issues as far as training and setting it up. So we always want to use a one-hot encoder if the values are not actual linear value or regression values, they're not actual numbers, if they represent a thing. And so now we need to go ahead and do our train X, test X, train Y, test Y, train split test data. And we'll go ahead and make sure it's going to be random, and we'll take 20% of it for testing and the rest for setting it up as far as training their model. This is something that's become so cool. When they're training these sets, they realize we can augment the data. What does augment mean? Well, if I rotate the data around and I zoom in, I zoom out, I rotate it, shear it a little bit, flip it horizontally, fill mode, as I do all these different things to the data, it is able to, it's kind of like increasing the number of samples I have. So if I have all these perfect samples, what happens when we only have part of the face, or the face is tilted sideways, or all those little shifts cause a problem if you're doing just a standard set of data. So we're going to create an augment in our image data generator, which is going to rotate, zoom, and do all kinds of cool things. And this is worth looking up, this image data generator and all the different features it has. A lot of times, the first time through my models, I'll leave that out because I want to make sure there's a thing we call build to fail, which is just cool to know. You build the whole process, and then you start adding these different things in so that you can better train your model. And so we go and run this, and then we're going to load. And then we need to go ahead, and you probably would have gotten an error if you hadn't put this piece in right here. I haven't run it myself because the guys in the back did this. But we take our base model, and one of the things we want to do is we want to do a MobileNet V2. And this is a big thing right here. Include the top equals false. A lot of data comes in with a label on the top row. So we want to make sure that that is not the case. And then the construction of the head of the model that will be placed on the top of the base model. We want to go ahead and set that up. And you'll see a warning here. I'm kind of ignoring the warning because it has to do with the size of the pictures and the weights for input shape. So it'll switch things to defaults, just saying, hey, we're going to auto shape some of this stuff for you. You should be aware that with this kind of imagery, we're already augmenting it by moving it around and flipping it and doing all kinds of things to it. So that's not a bad thing in this. But in other data, it might be if you're working in a different domain. And so we're going to go back here, and we have our base model. We're going to do our head model equals our base model output. And what we got here is we have an average pooling 2D, pool size 7.7 head model. Head model flatten, so we're flattening the data. So this is all processing and flattening the images. And the pooling has to do with some of the ways it can process some of the data. We'll look at that a little bit when we get down to the lower level and just processing it. And then we have our DINTs. We've already talked a little bit about a DINTs, just what you think about. And then the head model has a dropout of 0.5. What we can do with a dropout, the dropout says that we're going to drop out a certain amount of nodes while training. So when you actually use the model, it will use all the nodes. But this drops certain ones out, and it helps stop biases from forming. So it's really a cool feature in here. They discovered this a while back. We have another DINTs mode, and this time we're using softmax activation. Lots of different activation options here. Softmax is a real popular one for a lot of things, and so is ReLU. And we could do a whole talk on activation formulas and what their different uses are and how they work. When you first start out, you'll use mostly the ReLU and the softmax for a lot of them, just because they're some of the basic setups. It's a good place to start. And then we have our model equals model, inputs equals base model dot input, outputs equals head model. So again, we're still building our model here. We'll go ahead and run that. And then we're going to loop over all the layers in the base model and freeze them so they will not be updated during the first training process. So for layer and base model layers, layers.trainable equals false. A lot of times when you go through your data, you want to kind of jump in partway through. I'm not sure why in the back they did this for this particular example, but I do this a lot when I'm working with series and specifically in stock data. I want it to iterate through the first set of 30 data before it does anything. I would have to look deeper to see why they froze it on this particular one. And then we're going to compile our model. So compiling the model, atom, init, layer, decay, initial learning rate over epochs. And we go ahead and compile. Our loss is going to be the binary cross entropy, which will have that print out. Optimizer for opt, metrics is accuracy. Same thing we had before. Not a huge jump as far as the previous code. And then we go ahead and we've gone through all this, and now we need to go ahead and fit our model. So train the head of the network, print info training head, run. Now I skipped a little time because you'll see the run time here is at 80 seconds per epoch. It takes a couple minutes for it to get through on a single kernel. One of the things I want you to notice on here while it's finishing the processing is that we have up here our augment going on. So anytime the train X and train Y go in, there's some randomness going on there and is jiggling it around what's going into our setup. Of course, we're batch sizing it, so it's going through whatever we set for the batch values, how many we process at a time. And then we have the steps per epoch, the train X, the batch size, validation data. Here's our test X and test Y where we're sending that in. And this, again, it's validation. One of the important things to know about validation is when both our training data and our test data have about the same accuracy, that's when you want to stop. That means that our model isn't biased. If you have a higher accuracy on your testing, you've trained it, and your accuracy is higher on your actual test data, then something in there is probably has a bias and it's overfitted. So that's what this is really about right here with the validation data and validation steps. So it looks like let me go ahead and see if it's done processing. It looks like we've gone ahead and gone through 2 epochs. Again, you could run this through about 20 with this amount of data, and it would give you a nice refined model at the end. We're going to stop at 2 because I really don't want to sit around all afternoon, and I'm running this on a single thread. So now that we've done this, we're going to need to evaluate our model and see how good it is. And to do that, we need to go ahead and make our predictions. These are our predictions on our test X to see what it thinks are going to be. So now it's going to be evaluating the network, and then we'll go ahead and go down here, and we will need to turn the indexing, because remember it's either 0 or 1. It's 0, 1, 0, 1. So you have two outputs: not wearing a mask, not wearing a mask. And so we need to go ahead and take that argument at the end and change those predictions to a 0 or 1 coming out. And then to finish that off, we want to go ahead and let me just put this right in here and do it all in one shot. We want to show a nicely formatted classification report so we can see what that looks like on here. And there we have it. We have our precision. It's 97% with a mask. There's our F1 score, support without a mask, 97%. So that's pretty high setup on there. You know, three people are going to sneak into this store who are without a mask and thinks they have a mask, and there's going to be three people with a mask that's going to flag the person at the front to go, oh, hey, look at this person. He might not have a mask. That's I guess if it's a setup in front of a store. So there you have it. And of course, one of the other cool things about this is if someone's walking into the store and you take multiple pictures of them, you know, this is just it would be a way of flagging, and then you can take that average of those pictures and make sure they match or don't match if you're on the back end. And this is an important step because this is just cool. I love doing this stuff. So we're going to go ahead and take our model and we're going to save it. So model save maskdetector.model. We're going to give it a name. We're going to save the format. In this case, we're going to use the H5 format. And so this model we just programmed has just been saved. So now I can load it up into, say, another program. What's cool about this is, let's say I want to have somebody work on the other part of the program. Well, I just saved the model. They upload the model. Now they can use it for whatever. And then if I get more information and we start working with that, at some point I might want to update this model. Make a better model. And this is true of so many things, where I take this model and maybe I'm running a prediction on making money for a company, and as my model gets better, I want to keep updating it, and then it's real easy just to push that out to the actual end user. And here we have a nice graph. You can see the training loss and accuracy as we go through the epochs. We only did only shows just the one epoch coming in here, but you can see right here as the value loss, train accuracy, and value accuracy start switching and they start converging. And you'll hear converging. This is the convergence they're talking about when they say I know when I work in the scikit with sklearn neural networks, this is what they're talking about, a convergence, is our loss and our accuracy come together, and also up here, and this is why I'd run it more than just 2 epochs. As you can see, they still haven't converged all the way. So that would be a cue for me to keep going. But what we want to do is we want to go ahead and create a new Python 3 program. And we just did our train mask. So now we're going to go ahead and import that and use it and show you in a live action. Get a view of both myself in the afternoon along with my background of an office, which is in the middle still of reconstruction for another month. And we'll call this mask detector. And then we're going to grab a bunch of a few items coming in. We have our MobileNet v2 import preprocessing input, so we're still going to need that. We still have our TensorFlow image to array. We have our load model. That's where most of the stuff's going on. This is our CV2 or OpenCV. Again, I'm not going to dig too deep into that. We're going to flash a little OpenCV code at you, and we actually have a tutorial on that coming out. Our NumPy array, our IM utilities, which is part of the OpenCV or CV2 setup. And then we have, of course, time and just our operating system. So those are the things we're going to go ahead and set up on here. And then we're going to create, this takes just a moment, our module here, which is going to do all the heavy lifting. So we're going to detect and predict a mask. We have frame, FaceNet, MaskNet. These are going to be generated by our OpenCV. We have our frame coming in, and then we want to go ahead and create a mask around the face. It's going to try to detect the face and then set that up so we know what we're going to be processing through our model. And then there's a frame shape here. This is just our height versus width. That's all HW stands for. They've called it blob, which is a CV2 DNN blob form image frame. So this is reformatting this frame that's going to be coming in literally from my camera. And we'll show you that in a minute, that little piece of code that shoots that in here. And we're going to pass the blob through the network and obtain the face detections. So facenet.setImport blob, detections facenet forward, print detections shape. So this is what's going on here. This is that model we just created. We're going to send that in there, and I'll show you in a second where that is, but it's going to be under facenet. And then we go ahead and initialize our list of faces, their corresponding locations, and the list of predictions from our face mask network. We're going to loop over the detections, and this is a little bit more work than you think as far as looking for different faces. What happens if you have a crowd of faces? So we're looping through the detections and the shapes going through here. And probability associated with the detection. Here's our confidence of detections. We're going to filter out weak detection by ensuring the confidence is greater than the minimum confidence. So we've set it, remember, 0 to 1. So 0.5 would be our minimal confidence, probably is pretty good. And then we're going to put in compute bounding boxes for the object. If I'm zipping through this, it's because we're going to do an OpenCV, and I really want to stick to just the Keras part. And so I'm just kind of jumping through all this code. You can get a copy of this code from Simplilearn and take it apart, or look for the OpenCV coming out. And we'll create a box. The box sets it around the image. Ensure the bounding boxes fall within the dimensions of the frame. So we create a box around what we hope is going to be the face. Extract the face, ROI, convert it from BGR to RGB channel. Again, this is an OpenCV issue. Not really an issue, but it has to do with the order. I don't know how many times I've forgotten to check the order colors when working with OpenCV. Causes all kinds of fun things when red becomes blue and blue becomes red. And we're going to go ahead and resize it, process it, frame it, face frame setup. Again, the face, the CVT color, we're going to convert it. We're going to resize it, image to array, pre-process the input, pin the face, locate face, start X, start Y, and X. Boy, that was just a huge amount, and I skipped over a ton of it, but the bottom line is we're building a box around the face, and that box, because the OpenCV does a decent job of finding the face, and that box is going to go in there and see, hey, does this person have a mask on it? And so that's what all this is doing on here. And then finally we get down to this where it says predictions equals masknet.predict faces batch size 32. So these different images where we're guessing where the face is are then going to go through and generate an array of faces, if you will. And we're going to look through and say, does this face have a mask on it? And that's what's going right here is our prediction. That's the big thing that we're working for. And then we return the locations and the predictions. The location just tells where on the picture it is, and then the prediction tells us what it is. Is it a mask or is it not a mask? Alright, so we've loaded that all up. So we're going to load our serialized face detector model from disk. And we have the path that it was saved in. Obviously you're going to put it in a different path depending on where you have it or however you want to do it and how you saved it on the last one where we trained it. And then we have our weights path, and so finally our facenet, here it is, equals cv2.dnn.readnet prototext path weights path, and we're going to load that up on here. So let me go ahead and run that. And then we also need to, I'll just put it right down here. I always hate separating these things in there. And then we're going to load the actual mask detector model from disk. This is the model that we saved. So let's go ahead and run that on there also. So this is pulling in all the different pieces we need for our model. And then the next part is we're going to open up our video. And this is just kind of fun because it's all part of the OpenCV video setup. And let me just put this all in as one. There we go. So we're going to go ahead and open up our video. We're going to start it, and we're going to run it until we're done. And this is where we get some real, like, kind of live action stuff, which is fun. This is what I like working about with images and videos, is that when you start working with images and videos, it's all like right there in front of you. It's visual and you can see what's going on. So we're going to start our video streaming. This is grabbing our video stream source 0 start. That means it's grabbing my main camera I have hooked up. And then, starting video, you're going to print it out. Here's our video source equals 0 start. Loop over the frames from the video stream. Oops, a little redundancy there. Let me close. I'll just leave it. That's how they had it in the code. So while true, we're going to grab the frame from the threaded video stream and resize it to have the maximum width of 400 pixels. So here's our frame. We're going to read it from our visual stream. We're going to resize it. And then we have a returning. Remember, we returned from our procedure the location and the prediction. So detect and predict mask. We're sending it the frame. We're sending it the face net and the mask net. So we're sending all the different pieces that say this is what's going through on here. And then it returns our location and predictions. And then for our box and predictions in the location and predictions, and the box is again, this is an OpenCV set that says, hey, this is a box coming in from the location, because you have the two different points on there. And then we're going to unpack the box and predictions, and we're going to go ahead and do mask without a mask equals prediction. We're going to create our label. No mask, we're going to create color if the label equals mask L00225. And this is going to make a lot more sense when I hit the run button here. But we have the probability of the label. We're going to display the label and bounding box rectangle in the output frame. And then we're going to go ahead and show the output from the frame, CV2 IM show frame. And then the key equals CV2 wait key 1. We're just going to wait till the next one comes through from our feed. And we're going to do this until we hit the stop button pretty much. So are you ready for this? Let's see if it works. We've distributed our model. We've loaded it up into our distributed code here. We've got it hooked into our camera, and we're going to go ahead and run it. And there it goes. It's going to be running, and we can see the data coming down here, and we're waiting for the pop-up. And there I am in my office with my funky headset on. And you can see in the background my unfinished wall, and it says up here, no mask. Oh no, I don't have a mask on. I wonder if I cover my mouth, what would happen? You can see my no mask goes down a little bit. I wish I'd brought a mask into my office. It's up at the house. But you can see here that this says, there's a 95-98% chance that I don't have a mask on. And it's true, I don't have a mask on right now. And this could be distributed. This is actually an excellent little piece of script that you could start, you install somewhere on a video feed on a security camera or something, and then you'd have this really neat setup saying, hey, do you have a mask on when you enter a store or public transportation or whatever it is where they're required to wear a mask? Let me go ahead and stop that. Now, if you want a copy of this code, definitely give us a holler. We will be going into OpenCV in another one, so I skipped a lot of the OpenCV code in here as far as going into detail. Really focusing on the Keras, saving the model, uploading the model, and then processing a streaming video through it so you can see that the model works. We actually have this working model that hooks into the video camera, which is just pretty cool and a lot of fun. So I told you we're going to dive in and really roll up our sleeve and do a lot of coding today. We did the basic demo up above for just pulling in a Keras, and then we went into a Keras model where we pulled in data to see whether someone was wearing a mask or not. So very useful in today's world as far as a fully running application.
Sequential models in Keras. So what is Keras? Keras is a high-level Python deep learning API, which is used for easy implementation of neural networks. It has multiple low-level backends like TensorFlow, Thano, PyTorch, etc., which are used for fast computation. So you could think of this as Keras being almost its own little programming language, and then it sits on neural networks. In this case, the ones listed were TensorFlow, Thano, and PyTorch, which can all integrate with the Keras model. This makes it very diverse and also makes it very easy to use and switch around with different things. Keras is very user-friendly as far as neural network software goes as a high-level API. Computational graphs. So computational graphs are really the heart and soul of neural networks. We talk about a computational graph. They are a visual representation of expressing and evaluating mathematical equations. The nodes and data flow in a graph correspond to mathematical operations and variables. You'll hear a lot, some of the terms you might hear are node and edge, the edge being the data flow in this case. It could also represent an actual value. They have, I think in Spark they have a graph X, which works just on computing edges. There's all kinds of stuff that has evolved from computational graphs. We're focusing just on Keras and on neural networks. So we're not going to go into great detail on everything a computational graph does. It is a core component of a neural network, is what's important to know on this. So Keras offers a Python user-friendly front end while maintaining a strong computation power by using a low-level API like TensorFlow, PyTorch, etc., which use computational graphs as a backend. So one, this allows for abstraction of complex problems while specifying control flow. If you've ever looked at some of the backend or the original versions of TensorFlow, it's really a nightmare. You have all these different settings you have to put in there and create. It's a lot of back-end programming. This is like the old computers when you had to tell it how to dispose of a variable and how to properly reallocate the memory for use. All that is covered nowadays in our higher level programming. Well, this is the same thing with Keras, is it covers a lot of this stuff and does things for you that you could spend hours on just trying to figure out. It's useful for calculating derivatives by using backpropagation. We're definitely not going to teach a class on derivatives in this little video, but understanding a derivative is the rate of change. So if you have a particular function you're using in your neural network, a lot of them is just simple y equals mx plus b, your Euclidean geometry where you just have a simple slope times the intercept. And they get very complicated. They have the inverse tangent function for activation as opposed to just a linear Euclidean model. And you can think about this as you have your data coming in and you have to alter it somehow. Well, you alter it going down to get an answer, you end up with an error, and that error goes back up, and you have to have that back propagation with the derivative. You want to know how it changed so that you can figure out how to adjust it for the error. A lot of that's hidden, so you don't even have to worry about it with Keras. And in today's Keras, it'll even, if you create your own formula for computing an answer, it will automatically compute the derivative for you in a lot of cases. It's easier to implement distributed computation. So Keras is a really nice way to package it and get it off on different computers and share it. And it allows parallelism, which means that two operations can run simultaneously. So as we start developing these backends, it can do all kinds of cool things and utilize multiple cores, GPUs on a computer to get that parallel processing up. What are neural networks? Well, like I said, there are already, we talked about in computational edges, you have a node and you have a connection, or your edge. So neural networks are algorithms fashioned after the human brain, which contain multiple layers. Each layer contains a node called a neuron, which performs a mathematical operation. They break down complex problems into simple operations. So one, an input layer takes in our data and pre-processes it. When we talk about pre-processing, when you're dealing with neural networks, you usually have to pre-process your data so that it's between -1 and 1 or 0 and 1 into some kind of value that's usable. That occurs before it gets to the neural network. In fact, 80% of data science is usually in prepping that data and getting it ready for your different models. Two, you have hidden layer performs a nonlinear transformation of input. Now it can do a linear transformation. It can use just a basic Euclidean geometry, and you could think of a node adding all the different connections coming in. So each connection would have a weight, and then it would add to that weight plus an intercept in the node itself. So you can actually use Euclidean geometry. But a lot of these get really complicated. They have all these different formulas, and they're really cool to look at. But when you start looking at them, look at how they work. You really don't need to know the high math behind it to figure them out and figure out what they're doing, which is really cool. That means a lot of people can use this without having to go get a PhD in mathematics. Number 3, the output layer takes the results from hidden layer, transforms them, and gives a final output. So sequential models. So what makes this a sequential model? Sequential models are linear stacks of layers where one layer leads to the next. It is simple and easy to implement, and you just have to make sure that the previous layer is the input to the next layer. So you have used for plain stack of layers where each layer has one input and one output tensor, and this is what TensorFlow is named after. Is each one of these layers is like a tensor. Each node is a tensor, and then the layer is also considered a tensor of values. And it's used for simple classifier, declassifier models. It's also used for regression models too. So it's not just about this is something, this is a teapot, this is a cat, this is a dog. It's also used for generating the actual values. You know, this is worth $10, that's worth $30. The weather's going to be 90 degrees out or whatever it is. So you can use it for both classifier and declassifier models. And one more note when we talk about sequential models. The term sequential is used a lot, and it's used in different areas and different notations when you're in data science. So when we talk about time series, we'll talk about sequential. That is something very different. Sequential in this case means it goes from the input to layer 1 to layer 2 to the output. So it's very directional. It's important to note this because if you have a sequential model, can you have a non-sequential model? And the answer is yes. If you master the basics of a sequential model, you can just as easily have another model that shares layers. You can have another model where you have an input coming in and it splits. And then you have one set that's doing one set of nodes. Maybe they're doing a yes-no kind of node, where it's either putting out a 0 or a 1, a classifier, and the other one might be regression. It's just processing numbers, and then you recombine them for the output. That's what they call the Keras API. So there's a lot of different availabilities in here, and all kinds of cool things you can do as far as encoding and decoding and all kinds of things. And you can share layers and things like that. We're just focusing on the basic Keras model with the sequential model. So let's dive into the meat of the matter. Let's do a demo on here. Today's demo, in this demo, we'll be performing flower classification using sequential model in Keras. And we'll use our model to classify between 5 different types of flowers. Now, for this demo, and you can do this demo on whatever platform you want, or whatever user interface for developing Python, I'm actually using Anaconda, and then I'm using Jupyter Notebooks to develop in. And if you're not familiar with this, you can go under Environment. Once you've created an environment, you can come in here to open a terminal window. And if you don't have the different modules in here, you can do your Conda install, or whatever module it is. Just happened that this particular setup didn't have a Seaborn in it, which I already installed. So here's our Anaconda, and then I'm going to go back and start up my Jupyter Notebook, where I already created a new Python project, Python 3. I'm in Python 3.8 on this particular one. Sequential model for flowers. So lots of fun there. So we're going to jump right into this. The first thing is to make sure you have all your modules installed. So if you don't have NumPy, Pandas, Matplotlib, and Seaborn in the Keras, and sklearn, or Scikit, it's not actually sklearn, you'll need to go ahead and install all of those. Now, having done this for years and having switched environments and doing different things, I get all my imports done, and then we just run it, and if we get an error, we know we have to go back and install something. Right off the bat, though, we have NumPy, Pandas, Matplotlib, Seaborn. These are built on top of each other. Pandas, the data frame, and built on top of NumPy, the data array. And then we bring in our sklearn or scikit. This is the scikit setup, SCIKIT. Even though you use sklearn to bring it in, it's a scikit. And then our Keras. We have our pre-processing the images, image data generator, our model. This is our basic model, our sequential model. And then we bring in from Keras layers, import dense, optimizers. These optimizers, a lot of them already come in. These are your different optimizers, and it's almost, a lot of this is so automatic now. Atom is a lot of times the default because you're dealing with a large data. And then we get our SGD, which is smaller data, does better on smaller pieces of data. And I'm not going to go into all of these different optimizers. We didn't even use these in the actual demo. You just have to be aware that they are different optimizers. And the more you dig into these models, you'll hit a point where you do need to play with these a little bit. But for the most part, leave it at the default when you're first starting out. And we're doing just the sequential. You'll see here layers dense. And then if we come down a little bit more, when they put this together and they're running the dense layers, you'll also see they have dropout, they have flatten, they have activation, they have the convolutional layer 2D, max pooling 2D, batch normalization. What are all these layers? And when we get to the model, we're going to talk about them. A lot of times when you're just starting, you can just import Keras.layers, and then you have your dropout, your flatten, your convolutional neural network 2D. And we'll cover what these do in the actual example when we get down there. What I want you to take from here, though, is you need to run your imports and load your different aspects of this. And, of course, your TensorFlow TF, because this is all built on TensorFlow. And then finally, import random as RN, just for random generation. And then we get down here, we have our CV2. That is your open image, or your open CV, they call it, for processing images. That's what the CV2 is. We have our TQDM. The TQDM is for is a progress bar, just a fancy way of adding. When you're running a process, you can view the bar going across in the Jupyter setup. Not really necessary, but it's kind of fun to have. We want to be able to shuffle some files. Again, these are all different things. PIL is another image processor. It goes with the CV2. A lot of times you'll see both of those. And so we run those. We've got to bring them all in. And the next thing is to set up our directories. And so when we come into the directories, there's an important thing to note on here, other than we're looking at a lot of flowers, which is fun. Is we get down here, we have our directory archive flowers. That just happens to be where the different files for different flowers are put in. We're denoting an X and a Z. And the X is the date of the image, and the Z is the tag for it. What kind of flower is this? And the image size is really important because we have to resize everything. If you have a neural network, and if you remember from our neural networks, let me flip back to that slide. When we look at this slide, we have two input nodes here. With an image, you have an input node, depending on how you set it up, for each pixel. And that pixel has 3 different color schemes usually in it, sometimes 4. So if you have a picture that's 150 by 150, you multiply 150 times 150 times 3. That's how many nodes, input layers, coming in. I mean, so this is a massive input. A lot of times you think, oh yeah, it's just a small amount of data or something like that. No, it's a full image coming in. Then you have your hidden layers. A lot of times they match what the image size is coming in. So each one of those is also just as big. And then we get down to just a single output. So that's kind of a thing to note in here, what's going on behind the scenes. And of course, each one of these layers has a lot of processes and stuff going on. And then we have our different directories on here. Let me go ahead and run that. So I'm just setting the directories. That's all this is. Archive flowers, daisy, sunflower, tulip, dandelion, rose. Just our different directories that we're going to be looking at. And then we want to go ahead and we need to assign labels. Remember, we defined X and Z. So we're just going to create a definition here. And the first thing is return flower type. Okay, it just returns it what kind of flower it is, I guess, assign the label to it. But we're going to go ahead and make our train data. And when you look at this, there's a couple things to take away from here. The first one is we're just appending right onto our NumPy array the image. We're going to let NumPy handle all that different aspects as far as 150 by 150 by 3. We just dump it right into the NumPy, which makes it really easy. We don't have to do anything funky on the processing, and we want to leave it like that. And I'm going to talk about that in a minute. And then, of course, we have to have the string, append the label on there. And I want you to notice right here, we're going to read the image in, and then we're going to size it. And this is important because we're just changing this to 150 by 150. We're resizing the image so it's uniform. Every image comes in identical to the other ones. This is something that's so important is when you're resizing or reformatting your data, you really have to be aware of what's going on. With images, it's not a big deal because with an image, you just resize it so it looks squishy or spread out or stretched. The neural network picks up on that and it doesn't really change how it processes it. So let's go ahead and run that. And now we've got our definition set up on there. And then we want to go ahead and make our training data. So make the train data daisy flower, daisy directory, print length of X. So here we go. Let's go ahead and run that. And we're just loading up the flower daisy. So this is going all in there, and it's setting, it's adding it in to our setup on there, to our X and Z setup. And we see we have 769. And then, of course, you can see this nice bar here. This is the bar going across is that little added code in there that just makes it really cool for doing demos. Not necessarily when you're building your own model or something like that, but if you're going to display this to other people, adding that little, what was it called? TQDM. I can never remember that, but the TQDM module in there is really nice. And we'll go ahead and do sunflowers. And of course, you could have just created an array of these. But this has an interesting problem that's going to come up, and I want to show you something. It doesn't matter how good the people in the back are or how good you are at programming. Errors are going to come up, and you got to figure out how to handle them. And so when we get all the way down to the, where is it? Dandelion. Here's our Dandelion directory we're going to build. Jupyter has some cool things it does, which makes this really easy to deal with. But at the same time, you would want to go back in there depending on how many times you rerun this, how many times you pull this. So when you're finding errors going in here, there's a couple things you can do. And we're just going to, oh, it wasn't, there it is. There's our error. I knew there was an error. This processed 1,062 out of 1,065. Now, I can do a couple things. One, I could go back into our definition, and I can just put in here try, and so if it has a bad conversion, because this is where the error is coming from, just skip it. That's one way to do it. When you're doing a lot of work in data science, and you look at something like this where you're losing 3 points of data at the end, you just say, okay, I lost 3 points. Who cares? Or you can go in there and try to delete it. It really doesn't matter for this particular demo. And so we're just going to leave that error right alone and skip over because it's already added all the other files in there. And this is a wonderful thing about Jupyter Notebook is that I can just continue on there, and the X and Z, which we're creating, is still running, and we'll just go right into the next flower rows. So all these flowers are in there. That's just a cool thing about Jupyter Notebook. And then we can go ahead and just take a quick look and see what we're dealing with. And this is, of course, really, when you're dealing with other people and showing them stuff, this is just kind of fun where we can display it on the plot library here. And we're just going to go through and let's see, what do we got here? Looks like we're going to do like 5 of each of them, I think. Is that how they set this up? plot library 5 by 2. Okay, oh, I see how they did it. Okay, so 2 each. So we have 5 by 2 set up on our axes, and we're just going to go in and look at a couple of these flowers. It's always a good thing to look at some of your data. No matter what you're doing, we've reformatted this to 150 by 150. You can see how it really blurs this one up here on the tulip. That is at resize to 150 by 150. And these are what's actually going in. These are all 150 by 150 images. You can check the dimensions on the side. And you can see just a quick sampling of the flowers we're actually going to process on here. And again, like I said at the beginning, most of your work in data science is reprocessing this different information. So we need to go ahead and take our labels and run a label encoder on there. And then we're just going to, LE is a label encoder. One of the things we imported. And then we always use the fit to categorical, y comma 5, x, here's our array, x. So if you look at this, here's our fit. We're going to transform z. That's our z array we created. And then we have y, which equals that. And then we go ahead and do to categorical. We want 5 different categories. And then we create our x, NP array of x. X equals x over 255. So what's going on here, there's 2 different transformations. One, we've turned our categories into 0, 1, 2, 3, 4, 5 as the output. And we have taken our x array, and remember the x array is 3 values of your different colors. This is so important to understand. When we do this across a NumPy array, this takes every one of those 3 colors. So we have 150 by 150 pixels. Out of those 150 by 150 pixels, they each have 3 color arrays. And those color arrays range from 0 to 250. So when we take the x equals x over 255, range from 0 to 255, this converts all those pixels to a number between 0 and 1. And you really want to do that when you're working with neural networks. Now, if you do a linear regression model, it doesn't affect it as much, and so you don't have to do that conversion if you're doing straight numbers. But when you're running neural networks, if you don't do this, you're going to create a huge bias. And that means they'll do really good on predicting 1 or 2 things, and they'll just totally die on a lot of other predictions. So now we have our x and y values. X being the data in, y being our known output. And with any good setup, we want to divide this data into our training. So we have x train. We have our x test. This is the data we're not going to program the model with. And of course your y train corresponds to your x train, and your y test corresponds to your x test, the outputs. And this is, when we do the train test split, this was from the scikit, sklearn. We imported train test split. And we're just going to go ahead and do the test size at about 1/4 of the data, 0.25. And of course random's always good. This is such a good tool. I mean, certainly you can do your own division. You could just take the first 0.25 of the data or whatever, do the length of the data. Not real hard to do, but this is randomized so that if you're running this test a few times, you can kind of get an idea whether it's going to work or not. Sometimes what I will do is I'll just split the data into 3 parts, and then I'll test it on 2, with one being the, or I'll train it on 2 of those parts, with one being the test, and I rotate it. So I come up with 3 different answers, which is a good way of finding out just how good your model is. But for setting up, let's stick with the xtrain, xtest, and the sklearn package. And then we're going to go ahead and do a random seed. Now a lot of times the Keras actually does this automatically, but we're going to go ahead and set it up on here. And you can see we did an NP random seed from 42, and we get a nice RN number. And then we do TF random, we set the seed. So you can set your randomness at the beginning of your TensorFlow. And that's what the tf.random.set is. So that's a lot of prep. All this prep, and then we finally get to the exciting part. This is where you probably spend, once you have the data prepped and you have your pipeline going and you have everything set up on there, this is the part that's exciting, is building these models. And so we look at this model. One, we're going to designate it as sequential. They have the API, which is the Keras TensorFlow API versus sequential. Sequential means we're going one layer to the next. So we're not going to split the layer and bring it back together. It looks almost the same with the exception of bringing it back together. So it's not a huge step to go from this to an API. And the first thing we're going to look at is our convolutional neural network in 2D. So what's going on here? There's a lot of stuff that's going on here. The default for, well, let's start with the beginning. What is a convolutional 2D network? Well, a convolutional 2D network creates a number of small windows, and those small windows float over the picture, and each one of them is their own neural network, and it's basically becomes like a categorization. And then it looks at that and it says, oh, if we add these numbers up a certain way, we can find out whether this is the right flower based on this little window floating around, which looks at different things. And we have filters 32. So this is actually creating 32 windows, is what that's doing. And the kernel size is 5 by 5. So we're looking at a 5 by 5 square. Remember, it's 150 by 150. So this narrows it down to a 5 by 5. It's a 2D, so it has your x, y coordinates. And when we look at this 5 by 5, remember each one of these is actually looking at 5 by 5 by 3. So we're actually looking at 15 by 15 different pixels. And padding is just, usually I just ignore that. Activation by default is ReLU. We went ahead and put the ReLU in there. There's a lot of different activations. ReLU is for your smaller, remember I mentioned Atom, when you have a lot of data use an Atom kind of activation, or use an Atom processing. We're using the ReLU here. It kind of gives you a yes or no, but it doesn't give you a full yes or no. It has a 0 and then it kind of shoots off at an angle. Very common. It's the most common one. And then of course here's our input shape, 150 by 150 by 3 pixels. And then we have to pool it. So whenever you have a convolutional 2D layer, we have to bring this back together and pool this into a neural network. And then we're going to go ahead and repeat this. So we're going to add another network here. One of the cool things, if you look at this, is that as it comes in, it just kind of automatically assumes you're going down to the next layer. And so we have another convolutional neural network, 2D. Here's our max pooling again. We're going to do that again, max pooling. And we're just going to filter on down. Now, one of the things they did on this one is they changed the kernel size, they changed the number of filters, and so each one of these steps kind of looks at the data a little bit differently. And that's kind of cool because then you get a little added filtering on there. This is where you start playing with the model. You might be looking at a convolutional neural network, which is great for image classifications. When we get down to here, one of the things we see is flatten. So we just flatten it. Remember, this is 150 by 150 by 3. Well, and actually the pool size changes, so it's actually smaller than that. Flatten just puts that into a 1D array. So instead of being, a tensor of this really complexity with the pixels and everything, it's just flat. And then the dense is just another activation on there. By default, it is probably ReLU as far as this activation. And then, oh yeah, here we go. In sequential, they actually added the activation as ReLU. So this just, because this is sequential, this activation is attached to the dense. And there's a lot of different activations, but ReLU is the most common one. And then we also see a softmax. Softmax is similar, but it has its own kind of variation. And one of the cool things, you know what, let me bring this up because if you don't know about these activations, this doesn't make sense. And I just did a quick Google search on images of TensorFlow activations. I should probably look up which website this is. But this is the output of the values. So as it adds in all those weighted x values going into the node, it's going to activate it a certain way. And that's a sigmoid activation. And you can see it goes between 0 and 1 and has a nice curve there. This also shows the derivatives. And if we come down, the 7 popular activation functions, nonlinear activations, there's a lot of different options on this. Let me see if I can find the... Oops, let me see if I can find the specific to ReLU. So this is a leaky ReLU, and you can see instead of it just being 0 and then a value between going up, it has a little leaky there. Otherwise, your ReLU loses some nodes; they just become inactive. But you can see there's a lot of different options here. Here's a good one right here with the ReLU. You can see the ReLU function on the upper left here, and then the leaky ReLU over here on the right, which is very commonly used also. One of the things I use with processing language is the exponential one or the tangent H, the hyperbolic tangent, because they have that nice funky curve that comes in that has a whole different meaning and captures word use better. Again, these are very specific to domain, and you can spend a lot of time playing with different models. For our basic model, we'll stick to the ReLU and the softmax on here, and we'll go ahead and run and build this model. So now that we've had fun playing with all these different models that we can add in there, we need to go ahead and have a batch size on here, 128, epochs 10. This means that we're going to send 128 rows of data or flowers at a time to be processed. And the epochs 10, that's how many times we're going to loop through all the data. And then there's all kinds of stuff you can do. Again, this is now built into a lot of Keras models already by default. So there's different ways to reduce the values, and verbose equals 1 means that we're going to show what's going on. Value, what we're monitoring. We'll see that as we actually train the model. This is what's going to come out of there. If you set the verbose equal to 0, you don't have to watch it train the model, although it is kind of nice to actually know what's going on sometimes. And since we're still working on bringing the data in, here's our batch size, here's our epochs, we need to go ahead and create a data generator. This is our image data generator, and it has all the different settings in here. Almost all of these are defaults. So if you're looking at this going, oh my gosh, this is confusing, most of the time you can actually just ignore most of this. Vertical flip, so you can randomly flip pictures, you can randomly horizontally flip them. You can shift the picture around. This kind of gives you multiple data off of them. Zooming, rotation, there's all kinds of different things you can do with images. Most of these we're just going to leave as false. We don't really need to do all that setup because we already have a huge amount of data. If you're short data, you can start flipping like a horizontal picture and it will generate, it's like doubling your data almost. So the upside is you double your data. The downside is that if you already have a bias in your data, you already have 5,000 sunflowers and only 2 roses, that's a huge bias. It's also going to double that bias. That is the downside of that. And so we have our model compile, and this you're going to see on all the Keras. We're going to take this model here, we're going to take all this information as far as how we want it to go, and we're going to compile it. This actually builds the model, and so we're going to run that. And I want you to notice learning rate, very important. This is the default 001. You really don't. This is how slowly it adjusts to find the right answer. And the more data you have, you might actually make this a smaller number. If you have a very small sample of data, you might go even larger than that. And then we're going to look at the loss, categorical cross entropy, most commonly used. And this is how much it improves. The model's improving is what this number means. Or yeah, that's important on there. And then the accuracy. We want to know just how good our model is on the accuracy. And then one of the cool things to do is if you're in a group of people who are studying the model, if you're in shareholders, you don't want to do this, is you can run the model summary. I do this by default, and you can see the different layers that you built into this model. Just a quick summary on there. So we went ahead and we're going to go ahead and create a, we'll call it history, but we want to do a model fit generator. And so what this history is doing is this is tracking what's going on while it fits the model. Now there's a lot of new setups in here where they just use fit and then you put the generator in here. We're going to leave it like this, even though the new default is a little different on that. Doesn't really matter, it does the same thing. And we'll go ahead and just run that. And you can see while it's running right here, we're going through the epochs. We have 1 of 10, now we're going through 6 to 25. Here's our loss. We're printing that out so you can see how it's improving, and our accuracy. The accuracy gets better and better. And this is 6 out of 25. This is going to take a couple minutes to process because we are training 150 by 150 by 3 pixels across 6 layers or 8 layers, whatever it was. That is a huge amount of processing, so this will take a few minutes to process. This is when we talk about the hardware and the problems that come up in data science and why it's only now just exploding being able to do neural networks. This is why. This process takes a long time. Now you should have seen a jump on the screen here because I did pause the recorder to let this go ahead and run all the way through its epochs. Let's go ahead and take a look and see what these epochs are. And if you set the verbose to 0 instead of 1, it won't show what's going on in the behind the scenes as it's training it. So when we look at this epoch, 10 epochs, we went through all the data 10 times. If I remember correctly, there's roughly a gig of data there, so that's a lot of data. The first thing you're going to notice is the 270 seconds. That's how much each of those epochs took to run. And so if you divide 60 in there, you roughly get about 5 minutes worth of each epoch. So if I have 10 epochs, that's 50 minutes, almost an hour of runtime. That's a big deal when we talk about processing. On this particular computer, I actually have, 8 cores with 16 dedicated threads. So it runs like a 16-core computer. It alternates the threads going in. And it still takes it 5 minutes for each one of these epochs. So you start to see that if you have a lot of data, this is going to be a problem if you have a number of models. You want to find out how good the models are doing and what model to use. And so each of those models could take all night to run. In fact, I have a model I'm running now that takes about a day and a half to test each model. It takes 4 days to do the whole data. So what I do is I actually take a small piece of the data, test it out to find out, get an idea of how the different setups are going to do, and then I increase that size of the data and then increase it again, and I can just take that curve and kind of say, okay, if the data is doing this, then I need to add in more dense layers or whatever. So you can do a small chunks of data and then figure out what it costs to do a large set of data and what kind of model you want. The loss, as we see here, continues to go down. This is the error. This is how much error is in there. It really isn't a user-friendly number other than the more it trends down, the better. And so if you continue to see the loss going down, eventually you'll get to the point where it stops going down and it goes up and down and kind of wavers a little bit. At that point, you know you've run too many epochs. You're starting to get a bias in there, and it's not going to give you a good model fit. The accuracy just turns this into something that we can use. And so the accuracy is what percentage of guesses, in this case it's categorical, so this is the percentage of guesses are correct. Value loss is similar, it's a minus a value loss. And then you have the value accuracy, and you'll see the value accuracy is pretty similar to the accuracy, just rounds it off basically. And so a lot of times you come down here and you go, okay, we're doing 0.5, 0.6, 0.7. And that is 70% accuracy, or in this case, 68.59% accuracy. And that's a very usable number, and it's very important to have. If you're identifying flowers, that's probably good enough if you can get within a close distance and knowing what flower you're identifying. If you're trying to figure out whether someone's going to die from a heart attack or not, you might want to rethink it a little bit or rekey how you're building your model. So if I'm working with a group of clients, shareholders in a company or something like that, you don't really want to show them this. You don't want to show them, hey, this is what's going on with the accuracy. These are just numbers. And so we want to go ahead and put the finishing touches, just like when you are building a house and you put in the frame and the trim on the house. It's nice to have a nice view of what's going on. And so we'll go ahead and do a pie plot, and we'll just plot the history of the loss, the history of the value loss over here, epochs, train, and test. And so we're just going to compute these. This is really important. And what I want you to notice right here is when we get to about 5 epochs, a little more than 5, 6 epochs, you see a crossover here. And it starts crossing as far as the value loss. And what's going on here is you have the loss in your actual model and your actual data, and you have the value loss where it's testing it against the test data. The data wasn't used to program your model, wasn't used to train your model on. And so when we see this crossing over, this is where the bias is coming in. This is becoming overfitted. And so when you put these two together, right around 5 and 6, you start to see how it does this switch over here. And that's really where you need to stop, right around 5, 6. It's always hard to guess because at this point the model's kind of a black box. But you know that right around here, if you're saving your model after each run, you want to use the one that's right around 5 epochs because that's the one that's going to have the least amount of bias. So this is really important as far as guessing what's going on with your model and its accuracy and when to stop. It also is, I don't show people this mess up here. I show somebody this kind of model and I say this is where the training and the testing comes in on this model. It just makes it easier to see and people can understand what's going on. So that completes our demo, and you can see we did what we were set out to do. We took our flowers and we were able to classify them within about 68-70% accuracy, whether it's going to be a dahlia, sunflower, cherry blossom, rose. A lot of other things you can do with your output as far as different tables to see where the errors are coming from and what problems are coming up. Image classification using Keras. And we're going to take a look at image classification using Keras and the basic setup. And we'll actually look at 2 different demos on here. What's in it for you today? What is image classification? Intel image classification data, creating neural networks with Keras, and the VGG16 model. What is image classification? The process of image classification refers to assigning classes to an entire image. Images can be classified based on different categories like whether it is a nighttime or daytime shot, what the image represents, etc. And you can see here we have mountains looking for mountains. We'll actually be doing some pictures of scenery and stuff like that. In deep learning, we perform image classification by using neural networks to extract features from images and classifies them based on these features. And you can see here where it says like what computer sees, and it says, oh yeah, we see mostly forest, maybe a little bit of mountains because of the way the image is. And this is really where one of the areas that neural networks really shines. If you try to run this stuff through more like a linear regression model, you'll still get results, but the results kind of miss a lot of things as the neural networks get better and better at what they do with different tools we have out there. So Intel image classification data. The data being used is the Intel image classification data set, which consists of images of 6 types of land areas. And so we have forest, building, glaciers, and mountains, sea, and street. And you can see here is a couple of the images out of there as a setup in the Intel image classification data that they use. And then we're going to go into creating a neural networks with Keras. The convolutional neural network that we are creating from scratch looks as shown below. You'll see here we have our input layer. They have it listed max pooling. So you have, as you're coming in with the input layer, and the input layer is actually before this, but the first layer that it's going to go into is going to be a convolutional neural network. Then you have a max pooling that pools the convolutional neural network's returns. In this case, they have 2 of those. That is very standard with convolutional neural networks. One of the ones that I was looking at earlier that was standard being used by one of the larger companies, I can't remember which one, for doing a large amount of identification, had 2 convolutional neural networks, each with their max pooling, and then about 17 dense layers after it. we're not going to do that heavy duty of a code, but we'll get you headed in the right direction. And that gives you an idea of what you're actually going to be looking at when you look at the flattened part and then the dents. We're talking like 17 dense layers afterwards. I find that a lot of the stuff I've been working on, I end up maxing it out right around 9 dense layers. It really depends on what you have going in and what you're working with. And the VGG16 model. VGG16 is a pre-trained CNN model which is used for image classification. It is trained on a large, varied data set and fine-tuned to fit image classification data sets with ease. And you can see down here we have the input coming in, the convolutional neural network 1-to-1, 1-to-2, and then pooling. And then we do 2-to-1, 2-to-2 convolutional neural network, then pooling, 3-to-2, and you can see there's just this huge layering of convolutional neural networks. And in this case, they have 5 such layers going in, and then you have 3 dents going out or more. Now, when they took this setup, this actually won an award back in 2019 for this particular setup. And it does really good, except that, again, we only show the 3 dense layers here. And as you find out, depending on your data going in and what you have set up, that really isn't enough on one of these setups. And I'm going to show you why we restricted it, because it does take up a lot of processing power in some of these things. So let's go ahead and roll up our sleeves, and we're going to look at both the setups. We're going to start with the first classification, and then we'll go into the VGG16 and show you how that's set up. Now I'm going to be using Anaconda, and let me flip over to my Anaconda so you can see what that looks like. Now I'm running in the Anaconda here. You'll see that I've set up a main Python 3.8. I always put that in there because this is where I'm doing like most of my kind of playing around. This is done in Python version 3.8. We're not going to dig too much into versions. At this point you should already have Keras installed on there. Usually Keras takes a number of extra steps. And then our usual setup is the NumPy, the pandas, your scikit, which is going to be the sklearn, your Seaborn, and I'll show you those in just a minute. And then I'm just going to be in the Jupyter Lab where I've created a new notebook in here. And let's flip on over there to my blank notebook. Now, there's a couple cool things to note in here is that, one, I use the Anaconda Jupyter Notebook setup because it keeps everything separate, except for Keras. Keras is actually running separately in the back. I believe it's a C program. What's nice about that is that it utilizes the multiprocessors on the computer, and I'll mention that just in a little bit when we actually get down to running the code. And when we look in here, the couple things to note is here's our, oops, I thought I grabbed the other drawing thing. But here's our NumPy and our pandas right here and our operating system. This is our scikit. You always import it as sklearn for the classification report. We're going to be using, well, usually import like Seaborn brings in all of your PyPlot library also. Kind of nice to throw that in there. I can't remember if we're actually using Seaborn, if they just, the people in the back just threw that together. And then we have the sklearn shuffle for shuffling data. Here's our matplotlib library that the Seaborn is pretty much built on. CV2, if you're not familiar with that, that is our image module for importing the image. And then of course we have our TensorFlow down here, which is what we're really working with. And then the last thing is just for visual effect while we're running this. If you're doing a demo and you're working with the partners or the shareholders, this TQDM is really kind of cool. It's an extensible progress bar for Python. And I'll show you that too. Remember, data science is not, I mean, you know, most of this code, when I'm looking through this code, I'm not going to show half of this stuff to the shareholders or anybody I'm working with. They don't really care about pandas and all that. We do, because we want to understand how it works. So we need to go ahead and import those different setup on there. And then the next thing is we're going to go ahead and set up our classes. Now we remember if we had mountain, street, glacier, building, sea, and forest. those were the different images that we have coming in. And we're going to go ahead and just do class name labels, and we're going to kind of match that class name of I for I, class name equals the class names. So our labels are going to match the names up here. And then we have the number of classes, and print the class names and the labels. And we'll go ahead and set the image size. This is important that we resize everything, because if you remember with neural networks, they take one size data coming in. And so when you're working with images, you really want to make sure they're all resized to the same setup. It might squish them, it might stretch them. That generally does not cause a problem in these. In some of the other tricks you can do with, if you need more data, and this is one that's used regularly, we're not going to do it in here, is you can also take these images and not only resize them, but you can tilt them one way or the other, crop parts of them, so that they process slightly differently, and it'll actually increase your accuracy of some of these predictions. And so you can see here we have mountain equals 0, that's what this class name label is, street equals 1, glacier equals 2, buildings equals 3, C4, forest equals 5. Now, we did this as an enumerator, so each one is 0 through 5. A lot of times we do this instead as 0, 1, 0, 1, 0, 1, so you have 5 outputs and each one's a 0 or a 1 coming out. So the next thing we really want to do is we want to go ahead and load the data up, and just put a label in there, loading data. just so you know what we're doing, I'm going to put in the loading data down here. Make sure it's well labeled. And we'll create a definition for this. And this is all part of your pre-processing. At this point, you could replace this with all kinds of different things depending on what you're working on. And once you download, you can go download this data set, send a note to the Simplilearn team here in YouTube, and they'll be happy to direct you in the right direction. And make sure you get this path here, so you have the right, wherever you saved it. A lot of times I'll just abbreviate the path or put it as a sub thing and just get rid of the directory. But again, double check your paths. We're going to separate this into a segment for training and a segment for testing. And that's actually how it is in the folder. And let me just show you what that looks like. So when I have my lengthy path here where I keep all my programming Simplilearn, this particular setup we're working on, image classification and image classification. Clearly you probably wouldn't have that lengthy of a list. And when we go in here, you'll see sequence train, sequence test. They've already split this up. This is what we're going to train the data in. And again, you can see buildings, forest, glacier, mountain, sea, street. And if we double click, let's go under forest. You can see all these different forest images. And there's a lot of variety here. I mean, we have wintertime, we have summertime. So it's kind of interesting. You know, here's like a fallen tree versus a road going down the middle. That's really hard to train. And if you look at the buildings, a lot of these buildings, you're looking up a skyscraper, we're looking down the setup. Here's some trees with one, and I want to highlight this one. It has trees in it. Let me just open that up so you can see it a little closer. The reason I want to highlight this is I want you to think about this. We have trees growing. Is this the city or a forest? So this kind of imagery makes it really hard for a classifier. And if you start looking at these, you'll see a lot of these images do have trees and other things in the foreground, weird angles. Really a hard thing for a computer to sort out and figure out whether it's going to be a forest or a city. And so in our loading of data, one, we have to have the path, the directory. We're going to come in here, we have our images and our labels. So we're going to load the images in one section, the labels in another. And if you look through here, it just goes through the different folders. In fact, let me do this. There we go. As we look at this, we're just going to loop through the 6 different folders that have the different landscapes. And then we're going to go through and pull each file out and each label. So we set the label, we set the folder for file and list. Here's our image path, join the paths. This is all kind of general stuff, so I'm kind of skipping through it really quick. And here's our image setup. If you remember, we're talking about the images. We have our CV2 reader, so it reads the image in. It's going to go ahead and take the image and convert it to from blue, green, red to red, green, blue. This is a CV2 thing. Almost all the time it imports it, and instead of importing it as a standard that's used just about everywhere, it imports it with the BGR versus RGB. RGB is pretty much a standard in here. You have to remember that was CV2. And then we're going to go ahead and resize it. This is the important part right here. We've decided what the size is, and we want to make sure all the images have the same size on them. And then we just take our images and we're just going to append the image, append the label, and then the images is going to turn into a NumPy array. This just makes it easier to process and manipulate. And then the labels is also a NumPy array. And then we just return the output, append images and labels, and we return the output down here. So we've loaded these all into memory. We haven't talked much. There'd be a different setup in there because there is ways to feed the files directly into your Keras model. But we want to go ahead and just load them all because it's really, for today's processing and what our computers can handle, that's not a big deal. And then we go ahead and set the train images, train labels, test images, test labels, and that's going to be returned in our output append. And you can see here we did images and labels set up in there, and it just loads them in there, so we'll have these 4 different categories. Let me just go ahead and run that. So now we've gone ahead and loaded everything on there. And then if you remember from before, we imported, let me just go back up there, Shuffle. Here we go. Here's our sklearn utilities import Shuffle. And so we want to take these labels and shuffle them around a little bit, just mix them up so it's not having the same, if you run the same process over and over, then you might run into some problems on there. And just real quick, let's go ahead and do a plot so we can just, we've looked at them as far as from outside of our code. We pulled up the files and I showed you what that was going on. We can go ahead and just display them here too. And I tell you, when you're working with different people, this should be highlighted right here. This thing is like when I'm working on code and I'm looking at this data and I'm trying to figure out what I'm doing, I skip this process. The second I get into a meeting and I'm showing what's going on to other people, I skip everything we just did. So, and go right to here where we want to go ahead and display some images and take a look at it. And in this display, I've taken them and I've resized the images to 20 by 20. That's pretty small. So we're going to lose just a massive amount of detail. And you can see here these nice pixelated images. I might even just stick with the folder showing them what images we're processing. Again, this is, you gotta be a little careful of this. Maybe resizing it was a bad idea. In fact, let me try it without resizing it and see what happens. Oops. So I took out the image size and then we put this straight in here. One of the things, again, this is, put the D, there we go. One of the things, again, that we want to note whenever we're working on these things is the CV2, there are so many different image classification setups. It's really a powerful package when you're doing images. But you do need to switch it around so that it works with the PyPlot. And so make sure you take your NumPy array and change it to a uinteger8 format because it comes in as a float. Otherwise you'll get some weird images down there. And so this is just basically we've split up, or we've created a plot. We went ahead and did the plot 20 by 20, or the plot figure size is 20 by 20. And then we're doing 25, so a 5 by 5 subplot. Nothing really going on here too exciting, but you can see here where we get the images. And really when you're showing people what's going on, this is what they want to see. So you skip over all the code and you have your meeting, you say, okay, here's our images of the building. don't get caught up in how much work you do, get caught up in what they want to see. So if you want to work in data science, that's really important to know. And this is where we're going to start having fun. Here's our model. This is where it gets exciting when you're digging into these models. And you have here, there we go. When you have here, if you look here, here's our convolutional neural network 2D. And 2D is an image. You have two different dimensions, x, y, and even though there's three colors, it's still considered 2D. If you're running a video, you'd be convolutional neural network 3D. If you're doing a series going across a time series, it might be 1D. And on these, you need to go ahead and have your convolutional neural network. If you look here, there's a lot of really cool settings going on to dig into. We have our input shape, so everything's been set to 150 by 150, and it has, of course, three different color schemes in it. That's important to notice. Activation default is ReLU. This is small amounts of data being processed on a bunch of little neural networks. And right here is the 32. That's how many of these convolutional neural networks are being strung up on here. And then the 3 by 3, when it's doing its steps, it's actually looking at a little 3 by 3 square on each image. And so that's what's going on here. And with convolutional neural networks, the window floats across and adds up all these numbers going across on this data. And then eventually it comes up with 30, in this case, 32 different feature options that it's looking for. And of course, you can change that 32. You can change the 3 by 3, so you might have a larger setup. You know, if you're going across 150 by 150, that's a lot of steps. So you might run this as 15 by 15. There's all kinds of different things you can do here. We're just putting this together. Again, that would be something you would play with to find out which ones are going to work better on this setup. And there's a lot of play involved. That's really where it becomes an art form, is guessing at what that's going to be. The second part I mentioned earlier, and I can only begin to highlight this. When you get to these dense layers, one is the activation is a ReLU. They use a ReLU and a softmax here. It's a whole setup just explaining why these are different and how they're different, because there's also an exponential, there's a tangent. In fact, there's just a ton of these, and you can build your own custom activations depending on what you're doing. A lot of different things go into these activations. There are 2 or 3 major thoughts on these activations, and ReLU and softmax are, well, ReLU, you're really looking at just the number, you're adding all the numbers together and you're looking at Euclidean geometry, ax plus bx2 plus cx3 plus bias. With softmax, this belongs to the party of it's activated or it's not, except they call it softmax because when you get to 0, instead of it just being 0, it's actually a little bit less than 0, so that when it trains, it doesn't get lost. There's a whole series of these activations. Another activation is the tangent, where it just drops off and you have like a very narrow area where you have from -1 to 1, or exponential, which is 0 to 1. So there's a lot of different ways to do the activation. Again, we can do, that'd be a whole separate lesson on here. We're looking at the convolutional neural network, and we're doing the 2 pools. This is so common. You'll see two convolutional neural networks stacked on top of each other, each with its own max pool underneath. And let's go ahead and run that. So we built our model there, and then we need to go ahead and compile the model. So let's go ahead and do that. We are going to use the Atom optimizer. The bigger the data, the Atom fits better on there. There's some other optimizer, but I think Atom's a default. I don't really play with the optimizer too much. That's like once you get a model that works really good, you might try some different optimizers, but Atom's usually the most. And then we're looking at loss. Pretty standard. We want to minimize our loss. We want to maximize the loss of error, and then we're going to look at accuracy. Everybody likes to say accuracy. I'm going to tell you right now, I start talking to people and I'm like, okay, what's the loss on this and that? And as a data science, yeah, I want to know how the what's going on with that, and we'll show you why in a minute. But everybody wants to see accuracy. They want to know how accurate this is. And then we're going to run the fit. And I wanted to do this just so I can show you, even though we're in Python setup in here where Jupyter Notebook is using only a single processor, I'm going to bring over my little CPU tool. This is 8 cores on 16 dedicated threads, so it shows up as 16 processors. And actually, I got to run this and then move it over. So we're going to run this, and hopefully it doesn't destroy my mic. And as it comes in, you can see it's starting to go through the epochs. And I set it for 5 epochs. And then this is really nice because Keras uses all the different threads available. So it does a really good job of doing that. This is going to take a while. If you look at here, it's ETA 2 minutes and 25 seconds, 24 seconds. So this is roughly 2.5 minutes per epoch. And we're doing 5 epochs. So this is going to be done in roughly 15 minutes. I don't know about you, but I don't think you want to sit here for 15 minutes watching the green bars go across. So we'll go ahead and let that run. And there we go. There was our 15 minutes. It's actually less than that because I did, when I went in here, realize that, where was it? Here we go. Here's our model compile. Here's our model fit. And here's our epochs. So I did 4 epochs. So a little bit better, a little more like 10 to 11 minutes instead of doing the full 15. And when we look at this, here's our model. We talked about the compiler. Here's our history. We're going to history equals the model fit. We'll go into that in just a minute. And what we're looking at is we have our epochs. Here's our validation split. So as we train it, we're weighing the accuracy versus, you kind of pull some data off to the side while you're training it. And the reason we do that is that you don't want to overfit. And we'll look at that chart in just a minute. Here's batch size. This is just how many images you're sending through at a time. The larger the batch, it actually increases the processing speed. And there's reasons to go up or down on the batch size because of the smaller the batch. There's a certain point where you get too large of a batch and it's trying to fit everything at once. So 128 is kind of big. Depends on the computer you're on and what it can handle. And then of course we have our train images and our train labels going in telling it what we're going to train on. And then we look at our 4 epochs here. Here's our accuracy. We want the accuracy to go up, and we get all the way up to 0.83 or 83%. This is actual percentage based pretty much. And we can see over here our loss. We want our loss to go down. Really fluctuates. 55, 1.2, 0.77, 0.48. So we have a lot of things going on there. Let's go ahead and graph those. Turn that up. And our team in the back did a wonderful job of putting together this basic plot setup. Here's our subplot coming in. We're going to be looking at, from the history, we're going to send it the accuracy and the value accuracy labels and set up on there. And we're going to also look at loss and value loss. So you can see what this looks like. What's really interesting about this setup, and let me just go ahead and show you, because without actually seeing the plots, it doesn't make a whole lot of sense. It's just basic plotting of the data using the PyPlot library. And I want you to look at this. This is really interesting. When I ran this the first time, I had very different results, and they vary greatly. And you can see here our accuracy continues to climb. And there's a crossover here. Put it in here. right here is our crossover. And I point that out because as we get to the right of that crossover where our accuracy, and we're like, oh yeah, I got 0.8%, we're starting to get an overfit here. That's what this switchover means. As our value, as a training set versus the value accuracy stays the same. And so this is the one we actually really want to be aware of. And where it crosses is kind of where you want to stop at. And we can see that also with the train loss versus the value loss right here. We did one epoch, and look how it just flatlines right there with our loss. So really, one epoch is probably enough. And you're going to say, wow, okay, 0.8%. Certainly, if I was working with the shareholders, telling them that it has an 80% accuracy isn't quite true. And we'll look at that a little deeper. It really comes out here that the accuracy of our actual values is closer to 0.41% right here, even after running it this number of times. And so you really want to stop right here at that crossover. One epoch would have been enough. So the data is a little overfitted on this when we do 4 epochs. And, oops, there we are. Okay. My drawing won't go away. Let's see if I can get, there we go. For some reason, I've killed my drawing ability and my recorder. All right, took a couple extra clicks. So let's go ahead and take a look at our actual test loss. So you see where it crosses over. That's where I'm looking at. That's where we start overfitting the model. And this is where if we were going to go back and continually upgrade the model, we would start taking a look at the images and start rotating them. We might start playing with the convolutional neural network instead of doing the 3x3 window. We might expand that, or find different things that might make a big difference as far as the way it processes these things. So let's go ahead and take a look at our test loss. Now remember, we had our training data. Now we're going to look at our test images and our test labels for our test loss here. And this is just model evaluate, just like we did fit up here. Where was it? One more. Model fit with our training data going in. Now we're going to evaluate it on the, and this data has not been touched yet. So this model's never seen this data. This is on completely new information as far as the model is concerned. Of course, we already know what it is from the labels we have. And this is what I was talking about. Here's the actual accuracy right here, 0.48 or 4847. So this 49% of the time guesses what the image is. And I mean, really, that's the bottom dollar. Does this work for what you're needing? Does 49% work? Do we need to upgrade the model more? In some cases, this might be, what was I doing? I was working on stock evaluations, and we were looking at what stocks were the top performers. Well, if I get that 50% correct on top performers, I'm good with that. That's actually pretty good for stock evaluation. In fact, the number I had for stock was more like 30-something% as far as being a top performer stock. Much harder to predict. But at that point, you're like, well, you'll make money off of that. So again, this number right here depends a lot on the domain you're working on. And then we want to go ahead and bring this home a little bit more as far as looking at the different setup in here. And one of the, from sklearn, if you remember, actually let's go back to the top, we had the classification report. And this came in from our sklearn or scikit setup. And that's right here. You can see it right here on the, see, there we go. Classification report right here. sklearn metrics import classification report. That's what we're going to look at next. A lot of this stuff depends on who you're working with. So when we start looking at precision, this is like for each value. I can't remember what one was probably mountains. So if 44% is not good enough, if you're doing like you're in the medical department and you're doing cancer. Is this cancerous or not? And I'm only 44% accurate. Not a good deal. I would not go with that. So it depends on what you're working with on the different labels and what they're used for. Facebook, 44%, I'm guessing the right person. I would hope it does a little bit better than that. But here's our main accuracy. This is what almost everybody looks at. They say, oh, 48%, that's what's important. Again, it depends on what domain you're in and what you're working with. And now we're going to do the same model. Oops, somehow I got there it goes. I thought I was going to get stuck on there again. This time we're going to be using the VGG16. And remember, this one has all those layers going into it. So it's basically a bunch of convolutional neural networks getting smaller and smaller on here. So we need to go ahead and import all our different stuff from Keras. We're importing the main one is the VG16 setup on there. Just aim that, there we go. There's kind of a pre-processing images, applications, pre-process input. This is all part of the VGG16 setup on there. And once we have all of those, we need to go ahead and create our model. And we're just going to create a VGG16 model in here. Inputs, model inputs, outputs, model inputs. I'm not going to spend as much time as I did on the other one. We're going to go through it really quickly. One of the first things I would do is, if you remember in Keras, you can treat a model like you would a layer. And so at this point, I would probably add a lot of dense layers on after the VGG16 model and create a new model with all of those things in there. And we'll go ahead and run this because here's our model coming in and our setup. And it'll take it just a moment to compile that. Hey, what's funny about this is I'm waiting for it to download the package. Since I pre-ran this, it takes it about a couple minutes to download the VGG16 model into here. And so we want to go ahead and train features for the model. We're going to predict the train images, and we're going to test features on the predict test images on here. And then I told you I was going to create another model too, and the people in the back did not disappoint me. They went ahead and did just that. And this is really an important part. This is worth stopping for. I told you I was going to go through this really quick. So here's our, we have our model 2 coming in. And we've created a model up here with the VGG16, model equals model inputs, model inputs. And so we have our VGG16. This has already been pre-programmed. And then we come down here, and I want you to notice on this right here, model 2 layers -4 to 1, x layer x. We're basically taking this model and we're adding stuff onto it. And so we've just basically duplicated this model. We could have done the same thing by using model up here as a layer. We could have had the input go to this model and then have that go down here. So we've added on this whole setup, this whole block of code from 13 to 17 has been added on to our VGG16 model. And we have a new model with the layer, input, and x down here. Let's go ahead and run that and compile it. And that was a lot to go through right there. When you're building these models, this is the part that gets so complicated that you get stuck playing in, and yet it's so fun. It's like a puzzle. How can I loop these models together? And in this case, you can see right here that the layers, we're just copying layers over and adding each layer in. This is one way to build a new model. And we'll go ahead and run that. Like I said, the other way is you can actually use the model as a layer. I had a little trouble playing with it. Sometimes when you're using the straight model over, you run into issues. And it seems like it's going to work, and then you mess up on the input and the output layers. There's all kinds of things that come up. Let's go ahead and do the new model. We're going to compile it. Again, here's our metrics: accuracy, sparse categorical loss. Pretty straightforward, just like we did before. You got to compile the model. And just like before, we're going to create a history. The history is going to be new model fit train 128. And just like before, if you remember when we started running this stuff, we're going to have to go ahead and it's going to light up our setup on here. And this is going to take a little bit to get us all set up. It's not going to just happen in a couple minutes. So let me go ahead and pause the video and run it, and then we'll talk about what happened. Okay, now when I ran that, these actually took about 6 minutes each. So it's a good thing I put it on hold. We did 4 epochs. I actually had to stop it because it was at 10 and switch it to 4 because I didn't want to wait an hour. And you can see here our accuracy and our loss numbers going down. And just at a glance, it actually performed, if you look at the accuracy, 0.2658. So our accuracy is going down, or 26%, 34%, 35%. And you can see here at some point it just kind of kicks the bucket. Again, this is overfitting. That's always an issue when you're running on programming these different neural networks. And then we're going to go ahead and plot the accuracy history. We built that nice little subroutine up above, so we might as well use it. And you can see it right here. There's that crossover again. And if you look at this, look how the red shifts up, how our loss functions and everything crosses over. We're overfitting. After one epoch, we're clearly not helping the problem or doing better. It's just gonna baseline. This one actually shows with the training versus the loss, value loss. Maybe second epoch. So on here we're now talking more between the first and the second epoch, and that also shows kind of here. So somewhere in here it starts overfitting. And right about now you should be saying, uh-oh, something went wrong there. I thought that when we went up here and ran this, look at this, we have the accuracy up here is hitting that 48%, and we're down here, you look at the score down here, that looks closer to 20%, not nearly anywhere in the ballpark of what we're looking for. And we'll go ahead and run it through the actual test features here. And there it is. We actually run this on the unseen data and everything. 0.18 or 18%. I don't know about you, but I wouldn't want, at 18%, this did a lot worse than the other one. I thought this was supposed to be the super model, the model that beats all models, VGG16 that won the awards and everything. Well, the reason is that one, we're not pre-processing the data, so it needs to be more. There needs to be more as far as like rotating the data at 45-degree angle, taking partials of it, so you can create a lot more data to go through here, and that would actually greatly change the outcome on here. And then we went up here. We only added a couple dense layers. We added a couple convolutional neural networks. This huge pre-trained setup is looking for a lot more information coming in as far as how it's going to train. And so this is one of those things where I thought it would have done better. And I had to go back and research it and look at it and say, well, why didn't this work? Why am I getting only 18% here instead of 44% or better? And that would be why, is it doesn't have enough training data coming in. And again, you can make your own training data. So it's not that we have a shortage of data. It's that some of that has to be switched around and moved around a little bit. And this is interesting right here too. If you look at the precision, we're getting it on number 2, and yet we had 0 on everything else. So for some reason, it's not seeing the different variables in here. So it'd be something else to look in and try to track down. And that probably has to do with the input. But you can see right here, we have a really good solid 0.48 up here. And that's where I'd really go with, is starting with this model, and then we look at this model and find out, why are these numbers not coming up better? Is it the data coming in? Where's the setup on there? And that is the art of data science right there, is finding out which models work better and why. And we went through the very basics of convolutional neural networks along with the VGG16 import and how you can get started with that. And again, the art is the data going in and learning to play with it, find out what works.
And with that, we come to the end of this video on Keras. We really hope that you enjoyed this video. If you did, a thumbs up would be really appreciated. Also, here's your reminder to subscribe to our channel and click on the bell icon for more on the latest technologies and trends. Thank you for watching and stay tuned for more from Simply Learn.